reviews. So here we are on day 2. All right. Okay, so we talked about kind of modern terminology about clustering, cloud. We went through virtualization and talked about virtualization just as a general abstraction for operating systems versus process virtualization, which is really what containerization is. And then we talked at length about just the different types of hypervisors, which was just kind of a refresher so you can understand what the whole OS virtualization piece is and how that differs basically from containerization, which is not OS virtualization because it is actually relying on the kernel inside the host, right? And then we went through a lot of that at a high level, talked about the differences in sizes, the difference in vector and attack footprint, how it's easier to maintain containers because they don't have the usual swath of software. And then we talked about, just how Docker is like Kleenex or like Coke. It's like a popular synonym now for the actual technology, but it's not the actual technology. And we talked about some ancient, older. Did I say ancient? Oof, man, sorry. Didn't mean to be disruptive. About Solaris zones and OpenVZ, which is just there for historical reasons, and also that Docker Swarm used to be a strong competitor. They're still out, and Mirantis still owns them in the enterprise version at least. And Mesos and Marathon are still out, but Kubernetes has pretty much won the war. I just to mention this, just to qualify that just a little bit, is that Kubernetes might be winning the competition among all the advisors, but just to say this, and this is my individual perspective, Kubernetes has such a high learning curve, which is totally worth doing, but it's a different, it's a whole other set of infrastructure concerns. That what you're finding is people are learning Kubernetes and then they're figuring out how to give it to somebody else, right? They're figuring out how to get Amazon to run it or Azure to run it. Matter of fact, I just saw an announcement come in that Amazon just announced a new product called App Runner, which is where you give someone your container, you give Amazon, not someone, you give Amazon, you pay Amazon, right? Because they want your money. You give them your container and they will run Kubernetes for you. This is fully managed. This isn't partially managed, which is what the EKS service is, the Amazon Kubernetes service. So that's where Kubernetes is headed. So it's still very useful to learn how it functions, especially if you're running it on premise or on your local system. And it's going to be useful to understand how the underlying pieces work. But people more and more are trying to get managed service providers to take over Kubernetes because it is a pain. So it's a headache, and it's a worthy headache, but it's got a learning curve to it. And then we talked a little bit about microservices. I posted a link from Martin Fowler, who I used to work with at ThoughtWorks, just January, February. And Martin is an awesome signatory for the Agile Manifesto and a great thinker in general in the industry. But he's also an amazing architect, actually, and coder. So he talks a lot about microservices. So we mentioned that as kind of an adjunct to the whole concept. But there were two things really that were important to microservices. One I'll hold off because it's going to be a little quiz here in a second. Then we talked about Docker basics, just like the fundamentals of Docker. Where can you run Docker? What are the limitations, which we kind of touched on already? We talked about some of the client-side restrictions, such as for example, if you're running Windows and you want Docker Desktop for Windows, then you need to accept that VirtualBox is going to be disabled. If you don't care about that, then great, run it. Who cares? Move on. But if you do, then you might fall back to something like Docker Machine. And then we talked about the different components of Docker, right? Including just the Docker daemon, the containers themselves, images, which get stored in a local cache by the Docker daemon, and then also the registry, because hub.docker.com is the most famous registry in the world. And talked about a little bit about images, which actually, just so you know, can be exported as tarballs, like zip files almost, like tarballs. So if you want to export an image into a tarball, you actually can. Because remember, it's just a packaged file system. That's all it really is an image is just a packaged file system with apps in it. And then we talked about the difference between containers and images. And then we talked about the Docker file. And then we talked about like things that could be integrated with Docker, which was basically that anything that could run non-interactively on the command line, which is almost everything, frankly. We talked about the Docker run commands, and I did an abortive run of not being able to run in my environment because of being on Windows, but I fixed that yesterday. And you saw me actually run Ubuntu, but what we actually were doing is we were running the echo command from inside the Ubuntu container. Because remember, the Ubuntu kernel is not actually running, it's using the kernel of the host. So we were just actually running the echo command. Kind of, by the way, when you run a shell, it's the same thing. If you run bash, you're actually running bash on the kernel of the host, it looks like it's in the container and it's isolated to the container, right? Let's see. And then we went through a couple of like commands. Matter of fact, we threw up a bunch of JSON on the screen when we did inspect, and you saw far more information about a container than you ever really wanted to know, except when you're troubleshooting, right? And then we talked about volumes as a way of externalizing state, because Docker containers by default, when they are dropped and deleted, they lose their writable layer. It's deleted, right? And we talked about the Docker file with a capital D. And then we talked about Docker Compose, which Docker Compose was a way of orchestrating multi-level Docker containers that have to be orchestrated together, like a triple tier app or a web and database app, right? So that way you could do them together. We looked at Docker-compose.yaml and talked about how basically everything is now in YAML. Between YAML and JSON, you have it all. XML is hardly used at all anymore in most products. And then we broke down the actual Docker Compose file and talked about specifying services. And if we actually go back and look at the file, it's where we were breaking it down between which section is for this service, which section is for this service, where's the volume definition, that kind of thing. Oh, and we talked about how most of the containers will allow you to inject environment variables. And I referenced how when we get to Kubernetes, we actually do those through config maps, where we actually map files and values in the file system, and then they can just be read by the application, right? So it's not really an environment variable. If it is, it's set inside the container. And then we talked about managing Docker state, which again was basically just keywords for volumes. We just did volumes, we talked about volumes. We talked about, basically bind mounts, volumes themselves, which are all managed by Docker, and then tempfs. And then we talked about different storage drivers, like WA3003, which allows like containers to run on separate hosts. And I'm sorry, that's networking, right? But like WA3003 storage, device mapper, BTRFS, CFS, and BFS were basically just different file systems or ways of connecting to volumes. Sorry, there is an overlay networking driver as well. ZFS is like a really complex, like multi-RAID, multi-redundancy tool. BTRFS is just another flavor of file system that does some similar things. Device mapper allows you to do things like local loopback and whatnot. Virtual file system is the same. Those storage drivers were just different ways of mounting a volume inside of the container. We did talk briefly that remote data storage used to be a thing inside of Docker. We even clicked on RexRay and it said it's deprecated. There's a company called CloudStore, by the way, that is still doing Docker native drivers, but most people are doing Kubernetes drivers. They're not doing Docker drivers because no one's running Docker in production, not without an orchestrator. So, and then we talked about networking, which, there were several different varieties of networking. Do you want to make it look like the network card? Do you want to make it look like another computer attached to the network card? Do you want to overlay between hosts? Which, by the way, the overlay driver is used quite frequently by Kubernetes to make sure that containers like in pods can talk to each other. And then we talked about Mac VLAN, which allows you to actually make it look like you have a physical card. And there's a bunch of other third-party plugins. Most of this is being ignored in favor of Kubernetes networking, right? We talked about default bridge, which had some limitations to it, and then user-defined bridge, which you actually saw me create a bridge. By the way, I went back yesterday and I was like, oh, I misran. There's an LS. There's an LS network. Well, apparently when I went to do Docker network LS, I went Docker network create LS. So I created my own LS network. So I don't know. No one said anything, but someone was probably like, oh my God, what is this guy doing? He just like, that's not an LS. He just created an LS network. But no one said anything. So I was like, huh, I guess I just slid on by with my little demo faux pas there. But so it's Docker network LS, just to make sure we're clear. It's this. It's not what I was typing yesterday. So it's Docker network LS. So yesterday I actually typed Docker network create LS, and no one said anything. And then I was like, huh. I went back here yesterday. I was like, hey, look, there's an LS network actually in my thing. I was like, that's not what I wanted actually. So just to make sure, I was like, huh. So anyway, user-defined bridges don't have the same limitations as default bridge. You can actually remove, you can remove them from the network without having to restart containers. mainly people use the network command for isolation. I think it was a question that I think it was Chris or maybe John and I were talking about yesterday, is that it's mainly used for isolation. And then we talked about the open container initiative, which is basically a consortium of like I think it's Core OS, the Linux Foundation, Docker. That one I don't know as well because, quite frankly, no one really pays attention to it. They just adhere to the standards that they publish. They're not like monitoring them pretty closely. And then we talked about like the architecture for Docker, which was, interesting because it actually is remarkably like the way, let's see, Kubernetes actually uses it the same way. The only difference is that Containerd is also the default runtime for Kubernetes, but you could actually roll over to Creo if you wanted to. So you could basically use that particular specification if you wanted to. All right, so we talked about that link. We talked about Run C as a framework. Yeah, we talked about this container runtime interface plugin. And we put everything together. Oh, and we talked about how, like, for example, Containerd is the default for Kubernetes, so it's also the default for most of the cloud providers. Red Hat, by contrast, uses OpenShift, and their Containerd defaults to Creo, not to. And then someone asked, like, what's the functional difference? Nothing really, not at this point. There hasn't been enough differentiation because they both comply to the OCI standard. So I'm sure there's additional features in Creo because Red Hat tends to do that I'm not aware of. Which is, you might be like, Michael, didn't you work on OpenShift? You told us you worked on OpenShift. Yeah, but I didn't peel back the Creo specification. So there was nothing special in there that I think I remember standing out, but that could have changed. And that's what we did yesterday. Because things always change in this industry. We're always trying to keep up, right? So that was what we did yesterday. And we did a bunch of labs. We did like 6 labs on a variety of different topics, all covering fundamentals. Just refreshing how Docker functions, how to create containers, how to pull them down. And one command that usually stands out for students is Docker commit, because people don't realize that you can actually take a running container and commit that in as an image, right? So you could actually like modify and run your own if you want to. There is a process, I haven't done it in years, where you can actually take a running operating system and convert that into a container. But I haven't done that in a long time. But if we Google that, you can find actually where it's like, how do I convert my operating system into a running container? There are ways actually to do that. They're actually pretty simple. It's just size is the problem. Okay, so a couple questions for you. So yesterday when we talked, some of these, by the way, are going to be repeats, but I just kind of want to make sure you're paying attention. Is that yesterday when we talked about the difference between operating system virtualization and containers, I said that operating system virtualization is focused on the OS. Container virtualization is focused on what? What kind of virtualization actually is container virtualization? Yeah, good process virtualization. Now, just so you know, people are going to argue about it, and you know what? Like, let them. It's fine. Like, let them argue about it. It's okay, because people talk about containers as lightweight virtual machines, and they're not. They're actually, it's just a process. And by the way, you know what? I'm gonna see if I can dig that up. I remember I had an exchange actually with someone on Stack Overflow, and it was years ago. And I was like, oh, so explain to me how this works. And he actually showed me running Bash at RHEL version 7 and RHEL version 6 in a container, and apparently it broke with 6, and so like you couldn't actually run Bash on Ubuntu, like in an Ubuntu container inside of RHEL 6. Like if that was the host, for example, it would actually break. So I'll see if I can't dig that up, but it was actually pretty cool. I was like, oh, that shows very clearly that it's not running its own kernel. It's like, oh yeah, no, it isn't. Okay, so other questions? About what year, and I'll give plus or minus 1 on this, about what year did Docker first release out to the general public? Good. Yeah. And I'm going to take, there's 2 years that I'll accept as answers. It's the 2013, 2014 years, right? Because 2013 is technically when it came out. 2014 is about when it became like good enough for production use. Okay. Now, next question then, even though we're not on Kubernetes, What year did Kubernetes come out? Again, 2 years are possible answers from my perspective. Yeah, so Kubernetes was released to the public around the 2014-2015 timeframe. There was a version of it actually available prior to that, but it was very, very different. Google actually took a couple years to clean it up, package it, and make it more like consumable by the general public. So it's 2014-2015 is considered the year thereabouts. I think officially it was July 2014. So good. Okay. Question for you is that Creo and Docker, well, Docker belongs to Docker, but Creo and the whole OCI specification belongs to what particular consortium or what particular group of technologies? I mean, sorry, of companies. It belongs to a particular foundation. What foundation does the OCI specification belong to? No, Greg, that's a great guess. Unless it's changed, my understanding is that belongs to the Linux Foundation, right? So OCI belongs to the Linux Foundation. But Greg, you pre-answered my next question. So like where does Kubernetes belong? Right? Kubernetes belongs basically to the CNCF, right? And just to say this, basically everything belongs to the CNCF, even though the Linux Foundation owns the specification, everyone defers to the CNCF, right? As far as like what they're doing out with like containers and Kubernetes. Okay. Question. Actually, I don't know if I want to answer that. So what are some other container runtimes other than the ones that we've mentioned this morning that are like comparable or available? And they can even be deprecated. I'm not like super attached to that. But give me some other container runtimes that are out there other than Docker. Although it does have me curious, like what is the full list in 2021? What is the full list of container runtimes in 2021? Oops, not 20, whatever. Let's see. Well, we know Containerd, we know Docker, we know Creo, these container runtimes, right? There's others out there. What about Moby? Container runtimes. Moby used to be a container runtime. Is that still out there? Open framework to assemble specialized container systems. Yep. So Moby's still out there. What about Rocket? Rocket by OpenShift, or sorry, by Red Hat, right? Project was donated. This went to the CNCF. That's interesting. Oh yeah, that's a good point, Greg, because my Chromebook actually does the same thing, right? It does use LXC. Yeah. All right. So there are other container runtimes out there. Seems like for the most part, everyone kind of centers around Containerd, Creo, and Docker. So fair enough. Okay. Other questions? So if I want, and I'm going to move up a little ahead here. If I want to mount my local file system into a Docker container, what kind of volume mount is that? Bind mount, right, is the correct answer. Good. If I'm looking for a file system that I can mount and just dump a bunch of temporary data into, what kind of mount is that? Good. Greg's quick on the draw today. There it is. We got the answer. Good. So true or false, microservices and containerization are not good fits for each other when it comes to design and technology. Good. False. Excellent. Good. So let's talk about microservices for just a second, because this is a very simple definition. what is one of the key aspects of a microservice? The first one, actually, let me just give you one and then we'll get the other. The first one is that it governs one business domain, for example, of a product, right? So one like business domain of a product. So like, for example, customer profiling or inventory management, or we were looking at Netflix and it could be like, hey, Michael, continue watching, or hey, you might be interested in this, or hey, here's some new releases. Those are all microservices, right? Mainly recommenders, right? In the like ML, data science space. What is the other characteristic though, other than being part of one like business domain of a product? What's the other characteristic of a microservice that makes it a microservice? I mean, you could say like scalability, deployability, but I mean, there's something about the scalability and something about the deployability and something about the releasability. There's a quality to those that makes it a microservice as compared to a monolith. What is that? What's another way to say isolation? What's another way to? Good. Oh, we're right there. We're so close. Standalone. We're just dancing around the word, right? Well, maybe. Although you can run microservices without containers, although most of the time you wouldn't actually. But you do want it to be containerizable. That's actually a good question, Greg. We'll have to talk about what does it mean to be containerizable, right? But like we've got isolation, we've got standalone, independent, right? It's independent. It's basically independently scalable, independently deployable, independently releasable. It does not need another team, right? In order to do that. There's also typically a third quality that people don't necessarily talk about, but like in my conversations with like Martin, I'm like, hey, we're really missing this third thing. And the other thing is that how do these microservices talk to each other? Do they write big batch files and then FTP them to each other? Which, by the way, is still actually going on in companies, which shocks me to death. We're still FTPing files to each other. It's so weird. Anyway, Chris hit it right on the head. APIs. That's how we're talking to each other in this microservices world. If there's 20 microservices that make up a product, they are all talking to each other through an API. So here's a question for you. True or false? If I have a microservice that needs to get to another microservices database, it will go directly to that database. Is that true or false? Good. I love that. Because we're all over that. Yeah, false. No. Nobody touches the services database except for the service. If another service needs data from the database, it can actually go to the service and request the data, right? No one gets access to the database because in order to maintain independence, the only way another service can get to another service's data is through that service, because the API, right, is a contract in a way of like, hey, here's a published way you can get this information, right? Good. Okay. Now, if I wanted to isolate my WordPress containers that I'm running locally on my system, and I wanted to isolate them from, say, a triple tier app that I'm running over here that has like Tomcat on it, how could I create a partition between the two sets of containers on my local laptop? How would I partition them out so they couldn't actually talk to each other or see each other? Oh, Logan, yeah, you got it. Yeah, Greg, yeah, create a new network. Just put them on their own network. They're isolated. They can't see each other, right? Good. In Kubernetes, by the way, right, you can actually just do the same thing, just isolate them. You put them in different namespaces, is what you would do in Kubernetes, right? They wouldn't be able to see each other otherwise. Okay, excellent. Okay, so what is the largest size from a memory footprint that you can stick into a container? What's the largest size application? Like if I wanted to put Elasticsearch, which typically takes 32 gigs, sometimes 64, depending on how you have set up buffers. If I want to run Elasticsearch inside of a container, what is the largest memory footprint that I can run inside of a container? What's the limit? I'll give you a hint. It's a trick question. I love the I said it was a trick question. I got trick answers. Yeah. So, Chris, that's exactly right. And I think others kind of hinted around it as well, right? Is that the host system is the limit, right? Like just to say this, the FAA came to me and said, we have a 20-year-old application that we want to containerize, and we would like it to stick it out on a host. I said, oh, great. How big is it? And they said, well, it's about 128 gigs of memory. I was like, oh, what does it do? And then they're like, oh, it manages basically all of their traffic control stuff in the US. And I was like, oh, no, no, we're not. I'm not helping you with that. You can get somebody else to do that with you. I'm not doing it. That's like way too big. You should microslice that out. You should at least split it out into 2 monoliths that are smaller, maybe 4. Let's split this sucker out. And like make it tiny. But they were like, well, what's the problem? We can containerize 128 gigs. I was like, just because you can doesn't mean that you should actually. Like, what host are you going to put that on? It's going to have half a gig of memory, so you're going to run 4 of them. Like, I was like, like, no, that's ridiculous. We're not doing that. And I said, by the way, why don't you just refactor it? It's 20 years old, and by the way, it was a binary. It was like a ASP something, like a Windows binary, which I wasn't familiar with, and I was like, yeah, this is not for me. I would rewrite that whole thing and go. That's what we would do. So just because you can get to a 256 gig memory or half a gig of memory container doesn't mean you want to. And I will say that you probably will run into weird errors if you process virtualize 256 gigs or 512 gigs. Typically, at most you'll see sizes of, 128 megs to half a gig to a gig to 2 gigs to 4 gigs, sometimes 8 gigs. I've seen 16s and 32s. And of course, as memory gets bigger in footprint, you're going to see increased sizes on that. But typically, if it's around the 4 to 8 range, I start questioning if the service needs to be split into smaller, into a smaller subset. For example, I was working at a company where they had a billing system, and the billing system was 8 gigs, and we actually took it and made an American Express version and a PayPal version. And by the way, the teams were way happier because the code was kind of monolithic. So. No, Greg, it wasn't running COBOL. Although, I joke about this. COBOL can make a comeback here, along with Fortran. It's amazing how much money you can make if you know COBOL or Fortran or that stuff. It's crazy. Okay. All right. So, other questions. Let's see. So, if you wanted, and you weren't using Kubernetes, if you wanted to set the username and password for a container that had a database in it as it was booting, what would you use to do that? What would you set in the environment? So you got a Postgres database starting up. You're like, I need to set the username and password. How do I do that? Yeah, Greg, environment variables, right? So remember when we looked at it yesterday, if you go out and look at the container specification out there on hub.docker.com, and we look at Postgres, if we just go out there, like Postgres is, I think, a good example. If we just go out there and look at the Postgres container, remember there are instructions for how to manage this container out here, including how to start it. But look at this. See, oh, that's a little bit of an eye chart. Can we blow that up a little bit? See how this says Postgres password? They're setting the environment variable right on the command line, which, again, fine. It's still going to show up in history. But know as you go down, there's other environment variables. Postgres password, you can change set the user, database, other initialization arguments, right? Change the host auth method. So MySQL, by the way, is the same way. So are all the databases. Most of them have some kind of environment variables that you can set on boot, right, in order to set passwords. So most people aren't aware of that. So just know that, if you, that way you can change it yourself. Obviously, if it's got bash in there, you can always just Docker exec into the system in order to see what's going on. But just know that, especially for the data, the ones that have their own authentication mechanism, you can actually set the authentication details as environment variables. Good. Okay, what command would I type if I wanted to run Nginx? Leave the Docker off of it. Just type the verb and whatever else you need. If I wanted to run Nginx, what would I type? Docker something. So as the Docker start -d nginx run -p 8888, okay, nginx, good. I'm seeing some good things here. Let's see. Start. That one I'm not sure about actually. But hold on, Chris, that may actually work. Let's go take a look, assuming that Michael's not gonna flop back and forth. Oh, you didn't like that, huh? Wonder why you didn't like -d. Hold on, what am I missing here? Let's just do that. No such container in nginx. Well, that's interesting. Why is there no such container as nginx? Let's see. But there is an nginx container. Looks like it's up, right? There's an Ubuntu container. Looks like it's up, right? But it doesn't look like. Let's try this. Is it because of the name? Sorry, let me move this out of the way. There's other ways to do this, but I just want to make sure you see it. All right, what if I came back now and I renamed trusting sorry, past tense. All right, what if I renamed it and then I came in here and I already had an existing container and I typed in start nginx? Would that start it? Guess what? You did start it, but that's already an existing container, right? So if let's say I killed it and I just ran start. Interesting. Didn't I just kill that container? So I think if you already have an existing container, I think it'll work fine. But I think if you don't have nginx already running, I don't think start will work. So probably the like most proper command is going to be that run command, right? Oh yeah. By the way, Greg, when I found out that you could rename containers, I was so excited because I had started so many containers and they have those long weird names on them. Yeah, so it's awesome. But yeah, so Chris, for your command, it would work if you already had nginx downloaded and already been run. It probably would work, but otherwise, run is really the one you were looking at. Good. Okay, now you just saw start and stop. You just saw rename, by the way. What did I type just now in order to get that container to just stop? Like I made it cease. I destroyed it. What did I do there? Docker kill. Good. What if I wanted to remove the image off of the system? What would I type? Oh, interesting. Now, okay, good. Let's go take a look at that just to make sure that we're all on the same page, right? Wow, that desktop switch. All right, so let's say that is RMI like here right there? Oh yeah, it does require at least one argument. Does it know what I want? In this case, let's say it's nginx. There's a container using that as a reference. So that's one good thing to know is that if you have a running container referencing that image, you can't remove the image off, right? But let's say I was like, what do I have running right now? All right, you know what? Let's stop nginx. Actually, yeah, let's stop it. Let's stop nginx, and now I'm going to try and remove nginx. It's going to say, I still have a container that's stopped, but it's still there. What if I just delete nginx and it's gone? Can I remove the image now? Still having a problem. Why? Is there something still referring to it? Well, let's go see. Now, right now, it doesn't look like I have a running container. What do I need to do with Docker in order to show me all the containers that are on the system, not just the running ones? Good. All right, now look at this. I got a bunch of them now, right? But just to say this is that if I want to force that, right, I can just force it by putting a -f on there, right? If I want to force it, just be careful with that because then the container is not. You have to download it in order to start it back up again, right? Good. All right. If I wanted to create a volume, How would I do that? I'm just like softballing these up, aren't I? I'm not going to create a Greg network. That might lead to undesirable consequences. But you're technically correct, Greg. I get it. All right. What about if I want to do the same thing with a network? What do I do at that point? It's pretty much the same, right? Again, do you see that? Oh, now Chris, now you're creating Greg networks. That's awesome. So just know it's pretty much the same, and the commands are pretty much identical. Now, what are the two ways? And I don't need you to type the whole thing out. What are the two flags that I can put after Docker run to mount a volume? Like, what do I? What can I type in there? There's two flags that I can put on there. What are they? -v is one. What's the other one? It's mount, right? I think it's -- mount, if I remember correctly, right? -- mount will actually get you to mount. Now, I noticed that like Greg already posted the path. What are the three things that you need if you're going to do mount? I don't need you to type it out. Just give me the three like different fields. What are the three different key values I have to define for mount? Let's take two of these out. So we know that the source, the source and the destination must be set up. You can also do rewrite. What's the other thing that you need to define with mount that's not really defined with -v? Because we have tempfs, we have bind mounts, and we have volume mounts, right? So with mount, you also have to specify the type, right? Type equals bind, right? Source and destination equals, right, this. So good. All right. Oh yeah, and I think just a reminder, yesterday we were talking about, remember that Z? What particular security profile or security application do you need that Z at the end of your mount? It's not AppArmor. What's the other thing? Yeah, SE Linux. Yeah. So if SE Linux is enabled, you might need Z in order to get to work. Notice that I ran it without it yesterday, and it worked fine because I don't have SE Linux enabled on my Ubuntu server. Okay. Good. All right, let's stop there. I think that was a good review. Does anyone have any curiosities or anything for us to talk about? Anything that you want to dive into before we dive into Kubernetes for the rest of the day? Good. All right. Thank you for participating. If we were face to face, know that I would be giving out stickers for correct answers, but I can't do that yet. Someday, I'm gonna maybe start my own sticker provisioning company. It's gonna be the next new business model. Okay, let's talk about Kubernetes architecture. Oh, and let me go ahead and pre this up, because that's always a place we end up with this discussion. Okay. Okay, chapter 5. Here we go. So, Kubernetes, I think we talked about this already. It is Greek for helmsman, pilot, gubernatorial, or gubernatorial. It actually comes from the Greek there. So governor, right, is actually rooted against Kubernetes. I think someone feels like they made a mistake naming the project that long, because I personally don't have a problem with it. I mean, it's 10 letters long, but people were like, man, 10 letters is just way too long. So what they did is they cut out the middle 8 letters and they just call it Kates. So they take the 8 letters between U and E and they just take them out. And so you'll see it referred to as Kates all the time because people don't like typing Kubernetes, apparently. So that's where that came from, by the way. So people got lazy about typing Kubernetes, and so they just referred to it as Kates. We had a joke at I was at Honeywell a couple years back, and we just replaced all of our project names with letters, like with numbers. So like if the project name was Sentience, we just called it 7S7ZS, because it's like, really, you can just do that? But I mean, it made sense because like, who wants to type Kubernetes all the time? And Kube and K and whatnot is not specific enough for everyone to know what you're talking about. If you ever hop on the Slack channels for Kubernetes, you'll see people will like do like kube whatever, and it's like no, please use K8s, because otherwise it gets really confusing because there's so many tools out there like kubeflow and kubevert and all this other stuff. So this is a container orchestration system. This requires an operating system to run. So people are like, we don't need an operating system because we got containers. It's like, nope, still need an operating system. Kubernetes doesn't solve that problem. There are projects, by the way, to kind of tightly integrate things like Alpine and CoreOS in with Kubernetes. So it's like, sits on bare metal and it just goes to town. But it still requires some kind of operating system. So you just got to keep that in mind. So this is open source. It is owned by the CNCF. We've looked at the landscape for the CNCF. You've seen it, right? So you know that this is a core project. Now, and Greg put out an interesting thing, because like this is core, is that most of us will alias K to kubectl, so we don't have to type in kubectl. Well, oh, by the way, kubectl is frequently referred to as kubectl as well, which you'll see all kinds of like memes on kubectl, like cuttlefish and teddy bears and stuff like that. But usually we'll alias K to kubectl. If you ever take the CKA or the CKAD exam or the CK, I can't remember the name of the security specialist exam. Aliases are going to be your friends for a lot of commands. So we probably should talk about that at some point in time, maybe towards the end. But that's a common way to do it. So shortening the names is actually a common kind of like industry standard for dealing with Kubernetes. It's an open source system, came from Google. We talked about that. It actually came, originally it was called like the Borg project, or sometimes it was referred to as 7 of 9, which, by the way, if you look at the logo for Kubernetes, let's see. If you look at the like Kubernetes icon, for example, notice how it has 1, 2, 3, 4, 5, 6, 7 sides. That's a nod to Project 7 of 9. I guess the people who did this were kind of Voyager fans. And 7 of 9 was like one of the characters, like the Borg characters on there. And so the 7 sides of the icon, right, refer like are a nod to that older project. The obviously the wheel well also has 7 like kind of spokes, the steering wheel as well. And it basically is just referring to steering the container ship, right? Which is what the links are. So that's why the Kubernetes logo has 7 sides to it, because of a nod to the original project. Kubernetes likes to basically download and take your container, put it in its own not its own packaging for it, put it in its own partitions, its deployment partitions, and then it likes to move it wherever it needs to based on whatever policies you set, or if anything fails. Out of the box, Kubernetes will do amazing things for you without having to mess with the scheduler, auto recovery, any of that stuff. And it's real easy to scale applications because you just turn the dial on your replica set and say, look, I want to go from 4 to 8. And what will happen is that Kubernetes will download an additional 4 images onto 4 other systems if it has them. And by the way, Kubernetes will automatically maximize the spread of your containers across hosts, so that you don't have to worry about a host failing and taking out your entire infrastructure. So it's not going to stack all 8 of your deployments actually on one system. It's going to spread them around. And you can control that, by the way, with labels, right, and selectors inside of your pod specifications. Kubernetes will run on anything that has an operating system if it has the Linux kernel 3.10 and above. So you don't have to worry so much about where you would run it. The only catch is that Kubernetes is divided into primaries, formerly known as masters, and then nodes, which is like application nodes. Just know that the primaries only run Linux. You can't run primaries on Windows. You can't have like Windows masters, for example. You have to have Linux primaries or Linux masters. From the worker nodes, application nodes, those can be Windows, those can be Linux, doesn't matter. But just be aware, and they have no intention of converting those over to Windows. So just know if you're a Windows shop, you're still going to end up running some Linux boxes if you want Kubernetes. I did wonder that, Greg. So 5.12, that means 3.10 is ancient. That is ancient, actually. I can say that without offending anybody. That kernel is ancient. So container orchestration is the primary responsibility of Kubernetes. So regardless of where it runs, it's going to run the same. It's not going to run Kubernetes runs identically, whether it's on Linux hosts on virtual machines or whether it's on Linux hosts on bare metal. But it basically just runs like monitors containers. And when you tell it that you want 8, for example, it's going to keep 8 up. So if a host dies and takes 2 containers with it, it's going to run 2 more containers on another host with available capacity. So it's mainly for application clustering. And of course, it goes well with microservices for that very reason. Now, let's blow this up a little bit because that seems pretty tiny. Kubernetes is frequently divided up into 2 segments. There's the control plane, which Michael just used air quotes, the control plane, and then there's the data plane. The control plane is where the primaries or the masters live. The data plane is where all the containers live and where all the work actually happens at, right? So there's components, by the way, in the control plane, which basically meaning on the primaries or on the masters, including the API, which everything is interacts with the API, plus etcd, which is a data store, which we'll talk about in a second, plus a scheduler, plus if it's on a cloud provider and you make it cloud aware, it's going to have a cloud manager, and then there's also just the controller manager itself, right? There's just a controller there for a variety of different reasons for all the different like core components for Kubernetes. And so all of this is going to interact with the kubelet and with the kube proxy and any container runtimes that are actually on the node itself. Most of the time, the kubelet is what Kubernetes is interacting with on the actual worker nodes. Notice that the cloud provider is being managed by what's called the CCM, or the Cloud Controller Manager. There's a Cloud Controller Manager per cloud. So if you're on AWS, there's an AWS Cloud Controller Manager. If you're on Azure, there's a Cloud Controller Manager for that. And by the way, you can also extend it. There's actually, oh God, what do they call? What did AWS call it? I want to say it's like the cloud. Oh, I can't remember. I'm gonna have to look this up. It's like the Cloud Resource Manager. It's a way of extending Kubernetes to basically provision everything in your AWS environment. So like you could literally use a kubectl config, a Kubernetes like specification, like a YAML specification. You could actually start up AWS objects if you wanted to, right? Assuming that the cluster has permissions to start the objects in question. I think that's pretty nifty. I don't know that it really depends on your workflow. If you're using Terraform to do everything, then you're probably going to use Terraform to do everything. If you're using CloudFormation to do everything, you're probably going to use CloudFormation. If you're using Kubernetes to specify everything in your workflow, it might be cool to be able to specify cloud objects as well. But I don't know how that's going to get adopted widely, but we'll see. So we got the Cloud Controller Manager, etcd, the kubelets, the scheduler. I think we covered all the components. By the way, you can add additional components to the control plane just by inserting code into the API, right? You can extend it through operators and what they call custom resource definitions, or CRDs. Custom resource definitions allow you to create your own objects in Kubernetes and extend the API calls that you can make to the K8s API. So when you make a Kubernetes cluster, it always at a minimum includes one master or primary system and one worker node. Sometimes those nodes can be the same. Like if you're running Minikube, for example, or like I was running Kind earlier, it's actually all on the same host. Kind, by the way, stands for Kubernetes inside Docker. Minikube is just a way of running Kubernetes Dockerized inside of a single Linux machine. So that in and of itself is just a single node cluster. It's got the primary role and it's got the worker role all on it, right? Typically what happens is that with a cluster, you have at least one primary node and you've got multiple worker nodes. If you're in production, you're typically going to either run 3, 5, 7, 9. you're going to run an odd number of nodes, and it's all going to depend on what your architecture is set up as. For example, if you have 3 networks, you might run 3, 3, and 3, so that way if you lose a network, for example, you'll still have a quorum with 6 nodes remaining. So just know that the number of masters that you run, or primaries that you run, depends on the number of networks you have, right? If you got 4, you might run 2 in each one just for redundancy, right? Greg, the main reason is that you need to maintain a quorum. You can change the behavior, but you have to have a quorum, which means you have to have a majority, right, of the nodes. So for example, 9 will allow you to lose, 4 nodes before, right, you get a majority. And again, it just depends on your infrastructure setup. Yeah, for voting, for quorum, exactly. Just to say this, is that there's actually only one system out of all the primaries that's actually the master at any given time. That's like the leader. But the voting algorithm needs to have, a dominance, because they want to avoid what they call split brain, right? If a Kubernetes cluster somehow loses connectivity with each other, if it doesn't have a quorum or majority, it's not going to be authoritative for the cluster. And you might be thinking, Michael, that's weird. Split brain, by the way, is a problem that's been around for 30 years, right? It doesn't have anything to do with Kubernetes. It existed well before Kubernetes, but split brain is the standard problem that they're trying to solve. There was a PR for a long time to change the way that Kubernetes did that. As far as I know, that was never implemented, but they're still using a quorum method for resolving divisions between clusters. So typically there's at least one primary and one worker node, and that will make up your cluster. Usually in production, there's 3 primaries, and then at least typically 3 plus worker nodes. Now, I said this yesterday. Does anyone remember that with plain vanilla Kubernetes, what's the maximum number of worker nodes that you can have in a single cluster? It's one of those ridiculous numbers that it's like, really? But you can get pretty close to it. It's 5,000 worker nodes. So you can run 5,000 worker nodes in a single Kubernetes cluster. Now, you will have to scale up masters or primaries in order to support that, but just be aware that you can get up to 5,000 plain vanilla, and yeah, which is crazy. But by the way, you're typically limited to about 100 pods per node, even no matter what the size of the node is, right? Like obviously you have constraints around like memory footprint and disk space and stuff like that. But typically you're only going to get about 100 pods per node. You can push that to 200 just by changing a few limitations, but you're usually not going to get more than that, because you've got 200 virtualized processes that have their own overhead with CNAMEs and groups and stuff like that, and they're running their own networks, and they're coordinating with other nodes. So typically you're only going to get about 200 containers at most. Average is usually 100 on a particular Kubernetes like worker node. Notice it says worker node in parentheses. Okay. More than that, and you're going to need to change some limits. Now, containers are put into a deployment unit called a pod. And by the way, it says a group of 1 or more containers. Just to be clear, a pod typically only has 1 application container. It can have a security container. It can have a database container, as part of sorry, not a database container. Sorry, scratch that. Not a database container. A security container can have an operations container. It can have an authentication mechanism container using, for example, what they call sidecar proxying, right? And like Greg listed their sidecar pattern. But typically there's only 1 application container in a pod. Pods are what Kubernetes uses to deploy out across all of its systems. So when someone says, hey, I deployed 3 pods, that means you have 3 instances of your container running. They say 5 pods, you have 5 instances of your container running. But you're like, Michael, it says there that a pod is a group of 1 or more containers. Best practice, only stick 1 application container into a pod. But you're like, Michael, wait, what about if I want to, for example, just to annotate this for a little bit, like what if I want to, I've got my application here, and that's a container. And I actually want to stick a database in this whole thing. And I'd like to make it so that like this is the entire pod. And then that way I can just duplicate it if I need to scale it, right? But here's the problem. One, it depends on what kind of database you're using. But two, that means that if your application in red starts hotspotting, so you need to add more applications, you're going to be forced to duplicate the database by default, right? Because every time you deploy your app, you're going to have to deploy your database if it's in the same container. I'm sorry, pod, if it's in the same pod, right? Well, we don't want that. Like that doesn't work. We don't want to have to deploy this every time we deploy an application. So typically what you do is there's only one application in a pod. Pods get deployed. And by the way, if you need a database, that database goes in its own pod and you just call it through service discovery, right? And you just refer to it externally. And by the way, that's usually what's called the stateful set, which is different than the standard deployment of a pod, right? And that stateful set, by the way, has a persistent name. And no matter how many times that pod fails, it keeps the same name. So if the name is MySQL-0 and that pod fails and it restarts back up, guess what? It's MySQL-0. How do you persist the data? Well, we just saw that with with Docker, it's volumes. You attach a volume to the MySQL container so that when the pod fails and it comes back up, it has the same name and you can attach a volume to it so it has the same data, right? So that way you can restart that MySQL container all you want, that pod, if you will, and it's going to have the same data and the same name. That's really the only difference with stateful sets, which we're going to talk about at some point in time. But this is why you do not stick a database inside of your pod definition unless it's a separate independent pod that you're then going to refer to. So you're not going to stick your app and your database in the same pod. Those are two separate containers and they need to be in separate pods. Okay? And that's mainly because of the scale of the inefficiency of scaling those together. Now, that being said, let's say that we're in here and let's erase this. And we're like, you know what? But Michael, hold on. Operations wants me to run a service mesh. Well, guess what? You're going to have a little sidecar proxy here inside your pod, right? And then they come back and say, and you know, security wants me to have a little security scanner. So you might run that inside your pod, right? And then, you know, operators like you'll say, you know what, we have an authentication checker. We want you to run that as well. But note that the only one that is actually an application pod is this one. Everything else is just an adjunct to the application pod, or sorry, container, application container, right? So the rest of these are just operational containers, security containers, they're feature enhancement containers, but they're not the actual application. In a pod, there's usually only one application container. Does that make sense? Okay. Because when you deploy a pod, you're going to be deploying your containers. But the pod is the deployment segment. It's the deployment unit, if you will. And it's the smallest unit outside of the containers, right? And by the way, this isn't going to stop you if you decide that like, hey, I'd like to actually I want to SSH or bash directly into your operations container. Or you might say, you know what, I actually want to get connected to this proxy right here. You can still actually exec commands against specific containers inside of a pod. So don't worry about not being able to have access. And by the way, when you stick a bunch of containers inside of a pod, they have shared memory, shared storage, shared networking. So they're really they're kind of like tightly integrated and available to each other at that point in time, which is why this is ideal for a security, an operations, or a networking style containers attached to the application, because everything is so available, right? Think of this little pod boundary right here, this little green box. Think of it as like a security partition, right? Because it can act as a security partition. Good. Kind of leapt into. We're gonna go over that again, by the way. I just want to like preface it, like give you a little preview. Okay. Annotation can be fun. All right. So pod is a group of one or more containers created and managed by Kubernetes. Kubernetes manages pods and the containers that are inside of them. Container, we already know what a container is. We don't need to talk about that. We already know what a volume is, right? A volume is a directory of data that's accessible to containers within a particular pod, right? It shares, so a volume can share a lifetime with the pod that it's attached to. Sorry, a lifetime. I'm over here just making up stuff. A lifetime shares a life cycle. It can share a life cycle. So for example, if you attach a volume to a pod and you delete that pod, you can make it actually so that the volume deletes as well. Or, which is what most of us do, you make it so that the volume is independent. So if someone deletes the pod or the pod crashes, your data is still there, because that's why we create volumes. That's typically what we do, right? So just know the difference here is that with Docker, most of the time we were creating volumes that were our local file system. With Kubernetes, that game changes. Volumes can be NFS mounts. It can be EBS volumes if you're familiar with AWS. It can be anything you have a driver for. And Kubernetes has 10 times the drivers for remote storage than Docker does, right? Because Kubernetes is designed to make highly available storage available to the pods that sit inside the cluster. So just know we're going to talk more about that. So like we're just skimming the surface on that, but I'm just giving you a preview that volumes are far more robust in Kubernetes. Now, that being said, I want to make sure this concept is sliced up for you. So let's say that we have a bunch of boxes, and I'm going to choose pink because pink is a very manly color. So, right, here it is. Pink is a manly color, by the way. There's nothing wrong with wearing pink. Don't limit yourself. All right, so here you are, and someone comes in and says, you know what? I actually want to virtually isolate monitoring. Don't you like the little commentary that you get when you come to a technical class? Like I want to isolate my monitoring system with my, like, for example, MySQL database, or I have a triple tier app for project A and I don't want that to see my project B triple tier app, right? So consider these pink boxes, right, are actually like worker nodes that are in a cluster. So over here you got worker nodes, and up here on the right hand side, by the way, that's not a solid box, hold on. You've got your primary, formerly referred to as master node. So you got those up here on the right hand side. This whole thing is a cluster, by the way. All of this is cluster. So this whole thing in the upper right hand side, this is all the Kubernetes cluster. So I've got my 3 primaries and I've got a bunch of worker nodes. So if someone comes in and says, you know what, I want to isolate my applications from each other. I want to make sure that they can't see each other, right? And so what you do is that you can come in here and you can actually create what's called namespaces. And namespaces are little micro slices of your cluster. They're totally virtual. They run across all the worker nodes. Although, by the way, they also, just to give you a little preview, they actually do run across the primaries as well. But we're going to leave that alone for a minute. And so you can actually create namespaces, which actually create these virtual slices. And then here's where things get really interesting, right? Is that then you can actually run your containers inside these namespaces, and they are isolated from each other. Right? So consider the solid box as basically containers. And so I can actually run containers inside these namespaces, and they run on every system in the cluster, but they're segmented from each other. So you can make it so that the namespace is actually a security partition. Right? So for example, I can create a namespace for monitoring. I can create a namespace based on projects. I can create a namespace based on a particular development group, right? Because, you know, like people come up with crazy names for their, you know, their Scrum names, the Agile names for their like Scrum teams. And it's like, hey, the Crazy Eights, we're going to make sure that they have their own partition inside the Kubernetes cluster, right? And so namespaces are ways in which you can actually partition a cluster into like virtual clusters, basically. In addition, if you actually want to create other partitions, is that you can actually add labels to clusters. And labels, by the way, is like a type of metadata. You can actually add a label to a cluster. Actually, I don't want that there. And let's say, let me pick a good color here, that these systems here, the ones in red, those are Linux boxes. These over here are Windows boxes, right? And so what I can do is I can actually run my containers that I want on Windows. I can put a label on these boxes so that when the pod launches, I said, look, I only want nodes who have OS equal to Windows. That's where I want my containers to run. I can have another one that says, look, where the OS is equal to Linux, this is where I want my containers to run. You could do this for GPU boxes. Like I've done this I deal a lot with data science and machine learning teams, which I thoroughly enjoy, but they tend to be hogs. You know who you are on this call, right? They tend to be people who need things to go as fast as possible because they're training models and they're crunching data, right? And they're trying to like do it as fast as possible and in parallel if possible, right? So like I will give them dedicated like 20 like GPU instances in the cluster that they can run their stuff on just so they can do acceleration, right? And usually, by the way, there's usually a high number of CPUs as well as GPUs, right? And so I prefer to give teams their own dedicated cluster, but like if there's licensing issues or some kind of complexity issue, I will label the nodes in the cluster what their specialty is. So I'll have dedicated, for example, Linux GPU clusters, and all of my machine learning teams, when they deposit a container, it'll go on to that particular system. I have people doing .NET stuff and they need a Windows system. We'll do that as well. So just know that like we'll specify, the labels can allow you to specify where the container or /pod actually will run, right? Yeah, Greg, I want 80 CPUs on every box I'm running too. So just know that with labels and namespaces, you can actually control where stuff goes. Annotations, by the way, are different in that you have to have labels. Think of labels as tagging. You have to have labels to manage your system. Annotations can be used like to manage a cluster, but it's not really necessary. It's kind of like, it's just metadata. Now it can be informative, but it's not required. And then controllers, which we kind of like saw before. I'm gonna erase this. We saw controllers before. That's always so weird. This is a cloud controller. This is a controller manager. Controller manager is responsible for keeping these things up. That's the API server and the scheduler. A cloud controller manager is responsible for managing all objects that are created inside the cloud. So if you create a load balancer inside the cloud, this guy manages it. You create an EBS volume inside the cloud, this guy manages it. So the cloud controller is responsible for tracking the health of objects. And what will happen is sometimes the kubelet will ask something from this guy who will go and talk to the cloud provider and make an EBS volume and present it to the node, right? Or the kubelet will say, hey, I need a load balancer. They'll go talk to this guy who will respond back, and it will tell this guy, hey, you have a load balancer. Here's the DNS name and everything you need to know. So just note that controllers monitor the health of the objects they're responsible for. So if you have an Azure controller, it's responsible for Azure. If it's just the controller manager, it's just responsible for the controllers in general. So just be aware that that's what the controllers are there for. Good. Sorry, let me clear out all my drawings. All right. So now I just gave you a preview. We're going to run through that again. Okay. Clusters, you know what clusters are. We've been doing that all day long. The master nodes, again, I would prefer that you use the term primary, right? Or leader nodes if you want to. We're kind of moving away from that language with master nodes and minions and all the other stuff, like the whole master slave thing that's going away, right? We're not using that anymore. So the primary nodes actually manage the worker nodes, which sometimes is just referred to as nodes. You'll sometimes see the worker nodes referred to as minions, but we're moving away from that language as well. So the primary nodes are going to have several components. So you're going to have the API server, the controller manager, etcd, which maintains cluster state. So etcd, by the way, is a key value data store. And then the scheduler, by the way, is going to the scheduler is interesting. The scheduler judges the performance of the nodes and what their criteria is, and will help schedule pods and containers on the worker nodes. So the scheduler's job is to be like, hey, are you good enough for this pod? Because I only want the best for my pods, right? And so it's not that subjective, but that's what it does basically. As I said before, clusters can have more than one primary node, can only have one active leader node at a time. And if the leader is destroyed or taken offline, the remaining leaders will have or primaries will have a election to find out who's going to be primary, right? I was doing something the other day, and my girlfriend was listening to me, and she was like, "Wait, are you having elections over there?" I was like, "No, don't get excited. This is not a political election. There's nothing here worth talking about. It's just a bunch of technology, right?" She's like, "You geeks." The controller manager I mentioned before is responsible for node, like, basically has the node controller, has a replication controller. What's the replication controller? Replication controller is when you tell Kubernetes that you want 5 Nginx pods, it's the one that's responsible for making sure that replica set is 5, right? The whole set, the whole replica set is a number. And so its job is to make sure the replica set stays there. It'll also control like endpoints, like how like the API calls will like come in, for example. And then any service accounts that are created, because sometimes you might want to run things and they're not running as a user. They're running as a service account. By the way, here's a weird thing about Kubernetes. Kubernetes doesn't actually maintain a user database. It only recognizes users as authenticated objects. It doesn't actually have a user database. It maintains certificates. And if the certificate has a name in it, then that's how it identifies that as a user. But it doesn't actually have the concept of users and groups and stuff. Don't worry, it's got cluster roles and it's got permissions and it's got, cluster admin and all that stuff. But those are like permission sets. It doesn't actually have like a user database. It will hook into user databases, but Kubernetes, the community was like, we're not going to solve that problem. Someone else can do it. But they have certificates that represent users, which is really interesting, I think. Oh, by the way, there's also a token controller because it will sometimes grant permissions through tokens, right? Like you have a temporary token by which you can do something. You have to usually authenticate with a certificate first before it will give you a token. Sometimes it will give tokens to known services that have a certain like shelf life. One thing that I would be completely remiss, assuming I can talk, I would be completely remiss if I didn't mention this, is that if you ever want to really master Kubernetes, because you're going to be someone who's going to be running Kubernetes, like either on premise or some variation thereof, the best place to go like really learn how all this functions is that some of you may be familiar with a gentleman. Actually, move this off to the side. His name is Kelsey Hightower. He's a developer advocate for Google. He has a repository. It's actually a book called Kubernetes the Hard Way. And if you've never done this, this is an exercise. I'm gonna post this in the chat. This is an exercise in madness. First of all, you're utterly insane if you decide to do this, but you should if you are actually ever going to be administering Kubernetes, because what this will do, and notice, by the way, this is being maintained. So Kelsey is very much on top of this one. And by the way, if you've never seen Kelsey talk, he is hilarious and gives some of the greatest talks in the IT industry. He's also a very humble guy and very nice to deal with. Although every once in a while he blows up the Twitter space with his comments. So this basically is like for someone who's planning to support a production Kubernetes cluster and you want to understand how it fits together. This will teach you more about the internals of Kubernetes than you will want. At some point in time, it'll be like, who was that guy, the boxer who was like, no mas, no more hits, right? I can't take any more hits. This is like, it goes that deep. And basically what it does is it basically shows you how to put together everything you need in a cluster manually to put together your own Kubernetes cluster, right? Again, this is madness, but this will teach you more. And I've done this twice, actually. I actually run classes where we meet and run through this like weekly. It usually takes about 18 weeks to go through everything. It's just crazy. It will actually run on the GCP platform. You can just create a free account for that. It'll cost you a couple bucks. Some people have, by the way, ported this over to AWS and Azure, so you can find other copies of it as well. But this will like go through everything from like prerequisites, like what you need to set up in order to do it, installing the client tools, which ranges from kubeadmin to kubectl, right? How to do all this stuff, the conversion to JSON. It'll walk you through all that, and then it'll show you which compute resources like networking and whatnot that you need to provision, including firewall rules. So I just wanted to mention this, is that this would teach you more about how certificates, for example, function inside Kubernetes is crazy. And so this will teach all that. So I just want to make sure that you're aware of this. And to be honest, it takes 18 weeks because a lot of people show up and they don't actually do the work, and so we end up having to work in class. It doesn't actually take 18 hours to do this, but the problem is that when you do it in little chunks at a time and people are recontextualizing, it does take 18 weeks, give or take, right? But honestly, usually this will take a day. It'll take like 8 hours, and a lot of it's waiting. Like you're waiting for things to provision, you're waiting for things to start. You did this, you're coming back to this, you're doing this, you're coming back to this. It's really just a lot of waiting. So usually you can get this all set up and going if you're really focused in less than a day, right? Yeah, it's super manageable. It takes 18 weeks because of the recontextualization, right? When you do it with a group of people, and you know how it is. You'll have a group of people, and you might be the slow one that day, right? Like it's taking you longer to get through things. You got distracted for whatever reason. So, but usually it's 8 hours to run through this in detail. Yeah, super manageable. John, when's that class? Let me know if you're interested. Well, especially if I'll remind you, you can put it on the review, because if it's on the review, by the way, typically WebH will kick it off. So just so you know. Yeah, well, this definitely, like, you walk away with a deep understanding of Kubernetes by the time you're finished. This, by the way, is considered the holy grail of lingua franca for how if you want to master Kubernetes. This is have you done Kubernetes the hard way? That's usually going to be the first question they ask you, right? Is have you done? It's like the mythical man month, in IT. How many of you heard anybody refer to the mythical man month? Adding people to a project does not actually speed the delivery of that project. It's like that. Or the Phoenix project. If you haven't read the Phoenix project, that's another one that we run book clubs on. It's just tons of fun. Okay, we digress there because I just want to make sure that you had an opportunity for deeper exploration of these components. But we were on the control manager. Let me pause here for a second because I was talking a lot. Does anyone have any questions or curiosities? Anything that we need to talk about thus far? Okay, let's keep going then. We're definitely going to take a break after this. It's very heady. Okay, wait. Sorry, Michael hit the wrong button. Michael's made a mistake when he's talking about himself in the third person. Okay. All right. So nodes, we talked about worker nodes, application nodes, right? Remember, nodes are running a kubelet, which is basically just an API manager. It's like a controller, if you will, for the node. And they're running kube-proxy. The proxy allows the networking to happen inside Kubernetes. No proxy, no networking, right? So you have the kubelet. And by the way, what's the other thing that you know for a fact? If you're running Docker containers on the system, we talked about this earlier. What is the default thing that has to run if you're running Docker containers on a box? So if you got, well, definitely Linux, because you need an operating system, right? So you definitely have Linux on there because Kubernetes has to run on top of it. Yep, you have a Docker runtime, but it's not the Docker daemon. It's not the Docker engine, right? Which of the kind of runtime frameworks is it? Because it's not Creo. What's the other one? Containerd, right? It's Containerd. Good. Okay. By the way, if you're managing a Kubernetes cluster, everything can be seen through kubectl. So that kubectl command, which you're going to be touching later, you can see everything in kubectl, right? So, okay. So a pod is the unit of work / deployment on Kubernetes. When you want to deploy a container, you're going to deploy a pod. There are different kinds of deployments for a pod. There's different kinds. So there's a deployment, which makes it confusing because it's like, wait, a deployment is a kind of deployment? Yes, a deployment is a kind of deployment, right? Just like a cookie is a type of cookie, right? No, I'm just kidding. Let's not roll with that. So there is the deployments, right? There's also other things like jobs, which are also known as cron jobs. I don't know why they don't call them cron jobs. They should call them cron jobs because that's what they are. They're cron jobs, but we call them jobs. Just so you know. So there's deployments, there's jobs, there's stateful sets, which is the thing I was just referring to, which allows you to retain the name of a pod. So that, like, if the pod restarts, you don't lose the name. And then there's hold on, brain. Come on. Daemon sets. So daemon sets. Daemon sets. So you got jobs, so you got deployments, you have jobs, which are also cron jobs. Then you have stateful sets, and then you have daemon sets. Daemon sets are interesting because daemon sets run on every single node at least once. What do you use that for? You got a monitoring agent that you need for your node? Guess what? Run it as a daemon set. You need to get log files through Elasticsearch, like you're running FluentD or Logstash or something, and you need that to run on every node. Guess what? Run a daemon set. So just know that pods have a couple of different deployment types, and we are definitely going to talk about those again. Just giving you a preview. Now, pods are considered to be throwaway entities. Pods are ephemeral, meaning that you will destroy pods, you will redeploy pods. This is why this is a mutable infrastructure. Can you imagine if you had to configure your app at boot every single time? That's the difference, by the way, between a mutable infrastructure and mutable infrastructure, is that with mutable infrastructure, it changes over time. With a mutable infrastructure, it snapshots over time. In other words, the changes are snapshots. You're not actually changing it. Deploy, kill, deploy, kill, deploy, kill. I should use a better word for that. Stop, deploy, stop, right? So pods, just so you know, are basically the basic unit of deployment, and they have their own life cycle. Every pod is going to get its own unique ID. So it must be unique from everything else that is handled for you automatically, but just know there's going to be this randomization that happens, right? Pods, I love this. Pods are always scheduled together and always run on the same machine. I don't even know what that means, actually. You can just nix that whole phrase. When you run pods, they're actually scheduled one at a time. Like, for example, if you say I need 5 pods, it actually runs through the scheduling process one at a time, and then it will like kick them out to be scheduled. Now, it'll parallelize as much as it can, but they are not necessarily scheduled together per se, right? Every system is evaluated at the time that it's run. Usually there's only a millisecond difference between the scheduling process. They don't always run on the same machine, but all of the containers in a pod are always scheduled together, and they always run on the same machine. So that's probably what they were trying to say, is the containers in a pod are always scheduled together, and they are always run on the same machine. That's true. All the containers in a pod have the same IP address and port space. Hold on, I just need to make a note to correct this slide. All the containers in a pod have the same IP address and port space, which means that, like, if it's a 172 like 16 dot blah blah blah, to get to any of the containers in that pod, it's 1716 dot blah blah blah, which of course, you know, that's the official number, right? And what you would do is, if you need to get to the ports, the containers are all going to expose different ports, so you just hit the port number. You can get inside of a pod if you need to in order to get to other things, but usually what you're going to do is you're going to get inside of a container, and then you're going to get to the other containers from that container, right? So, but you can just attach to containers directly if you want to. Containers within a pod, because they share the same networking stack and the same memory space, they either communicate by doing a loopback on like a 127 like loopback to a different port, or they just attend to memory directly because they're sharing the same memory space. So even though they're containerized, they can actually share interprocess space with each other, which is typically, again, there's only usually one application in a pod. So what we're talking about is operational security, networking kind of additional pods that are kind of all linking in to this application pod, right? So like, for example, service mesh uses that sidecar pattern that Greg was talking about earlier. And that sidecar pattern basically inserts Envoy in as a sidecar pattern with the application container. Let's actually take a look at that so that we can see what that looks like. Yeah, let's do an example. I love that. Give me an example of a sidecar pattern. Okay, So, da, 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 da. All right, let's see. So I'm still looking for one. Here we go. Here's the streaming sidecar pattern. Okay, so this is interesting. Let's blow this up a little bit. So this, by the way, is logging, right? And what's happening here is, let me bring up my annotation bar. This is the pod in red. This is the app container. Now, don't get me wrong. There's traffic coming into this app container that has nothing to do with logging. So, right, there's traffic hitting this app container through the pod boundary, right? Through this pod boundary, they're hitting the app container because the port's being exposed, right? And there might even be a load balancer over here, just to be clear. There could be a load balancer that's accepting traffic, and in exchange, there's traffic hitting the load balancer, and the load balancer is hitting the app container, right? Because that's what load balancers do, right? They accept traffic on our behalf, and then they distribute it to a bunch of backends. So there could be, for this app container right here, there could be 10 of these, and they're all receiving traffic from this load balancer. Now, inside the pod, though, what's happening is that there is this little streaming container here. And what's happening is that this app is actually sending its logs to this streaming container. And it's actually streaming everything out to this log file. And there's a log agent pod. Let's say it's a daemon set, for example, on the host that's actually grabbing this log file and then sending it off to the back end. Like it's sending off, let's say it's Elastic, the Elastic Stack, right? Elasticsearch, Logstash, Kibana, or Elasticsearch Fluentd in Kibana. And so what's happening is this logging agent on the actual node is actually just sending the streaming information. So there's this whole chain of events that's happening where it's streaming from the app container into the streaming container. It's actually streaming the log file right out, let's say the local file system. This is being picked up by an agent, right? And so this guy, the app container, is never being overloaded with having to buffer, hold, or cache the log files. It's immediately streaming them out to the streaming container, right? And so, and by the way, the streaming container is just writing the standard error or standard out. Because just so you know, everything that is kit to standard error and standard out is typically written in Kubernetes to a log file that is actually on the local host file system, on the nodes file system, which is why you have an agent over here that's picking up those log files and pushing them out to a backend. Because if this pod goes away, guess what happens to this log file? It goes away too, right? So this is why you want a streaming agent that's actually out here gathering, buffering, writing to the log file, and then you have something else gathering the log files and sending out. So the important point to all this, before I cluttered it up with all my drawings, is that this streaming container sits inside the pod boundary. It is co-located inside this pod. And so it's accepting and connecting to traffic in shared memory space with this actual app container. That's the sidecar pattern, is to have it inside. Let's look at another example, assuming that Michael can remove all his drawings. Let's look at another sidecar pattern. Is that a good one? Sidecar container, application container. That's actually not bad, right? It shows this just a generics as far as sidecar. Let's look at another one. Daemon set mode, sidecar mode. I've looked at that already. Don't see another good one. Hold on one second. I'd like to come out here and randomly see what's available. There's another one that has the sidecar container with the main container. I'm trying to find something a little bit more specific. Service mesh. Ooh, that's a good one. Hold on. Service mesh. That's a good one right there. Let's pull this one up. This is by Weaveworks, by the way. Weaveworks partners with AWS to do a lot of their Kubernetes stuff. Weaveworks does also a lot of GitOps. So if you're a DevOps person, they're actually pretty good to look at. So here, by the way, is an ingress gateway that's going to a front end and back end in the database. And then, by the way, here's an egress gateway. This handles north-south traffic. This handles east-west traffic. So there's no security between these services, right, in this particular case. So what they've done is they've made it so that this ingress gateway is actually writing to a proxy, which is actually inside the pod itself. And so in this particular case, the traffic's coming in and it's actually hitting the proxy. This traffic here is encrypted. Now it's encrypted. Before it wasn't encrypted. And by the way, the traffic between the proxy and the front end, that's unencrypted. So the developer didn't have to worry about how that traffic was going to be encrypted. And we didn't. And how did we solve this? We solved this operationally. We stick a proxy inside there, and we actually set up encryption at the proxies level. And so the developer doesn't have to worry about this at this level. Maybe the service doesn't support it. Maybe it requires additional coding. And like we can just leave developers honestly to do what they need to do, which is feature development, right? And not have to like force them to, like, maybe we're out of time or we're constraining our resources. We're like, look, we got to encrypt this. We got auditors coming. It's like, well, guess what? We will stick a proxy here, create a service mesh, and we will encrypt that traffic. And guess what? We don't have to eat any developer time whatsoever. We don't have to maintain the ciphers with developer time. We don't have to renew the certificates with developer time. We can just let it handle that operationally, and we can actually set it to automatically refresh most of that, right? This is where the sidecar pattern becomes really handy, is that the sidecar can become the primary traffic director. It can be the primary security scanner. It can be the primary log director. It can be the primary operational center inside the pod itself. Does that make sense to everybody? Was that new to everybody? Hopefully that was new to everybody. Like people were like, I had no idea that you could even do that, Michael. Right? Good. This, by the way, remember I told you like what's the next thing after Kubernetes? Service mesh is kind of like the next smaller thing they're putting on top of Kubernetes. So just be aware. And that's all it is. Service mesh is just creating a bunch of sidecar proxies that all talk to each other. Right? Cool. And so can you imagine if you have 1,000 applications that all have proxies and they're all able to like mesh with each other? That's where the service mesh concept comes up. Good. Okay, let's go back. So we talked about pods. So again, remember, containers inside of a pod share the same networking and memory space. Well, not 100% the memory space, but they can see each other. They can talk to each other process-wise, right? By the way, if shared local storage is put into the pod, all the containers can see it, right? Which is also good if you have a little security sidecar in there scanning the file system to make sure there's no PII or anything weird in there. You can do that as well, right? Now, use pods to group containers. No, you're not doing that. You are grouping operational security containers in with your application pod, but you are not going to group multiple application pods. Remember, it's the Highlander rule. I know that's an older movie. I know I saw it when I was really, really young. But the Highlander rule is that there can be only one, right? There can only be one Highlander. So there can only be one application container inside of your pod. I've referred to this earlier, switching a little bit off of pods and containers for a moment, is that labels are basically key value pairs that you can use to basically categorize and manage your objects. I gave the node example, which is like I have Linux nodes and I have Windows nodes, right? But you can have other examples that might make sense to you. Labels are important for things like replica sets, services. They actually use the labels to find apps. Like if the label was labeled Nginx and you created a service, the service would literally look for the pod where it had a label, an app name equal to Nginx. So labels are most of the time handled automatically for you, but you want to have also your own labels. Like for example, how do you know all the production pods if you're mixing production and whatnot together? How do you know all the project pods for a particular product, right? Pods can have multiple labels. There are like weird limitations, like 256 characters for this, that, and the other. Most of us are not writing a novel in our labels, so there's plenty of space in there. Each label on a pod must have a unique key. You can't have app equals something, app equals something, app equals something. You can only have one instance of app equals. The key, which is the first part, has to be unique on the particular object. So you can't have duplicative keys on a pod or on a node or whatever. Note, but that by the way, like you can have a prefix, like colon dash, like you can have prefixes, like it's usually preceded by a /, just so you know. And it has to be a valid DNS subdomain, which I think is super interesting. Like it has to be like Kubernetes.io or objects.kubernetes.io, right? You'll see this in the lab, by the way. This prefix has to be at most 253 characters long, but the key name, which is different from the thing before the slash. Before the slash is just a prefix, right? The name itself at most can be 63 characters long. I don't know why it's 64 minus 1. I have no idea. But it's got to start with an alphanumeric character and can only contain alphanumerics, dots, dashes, and underscores. So dot, dashes, and underscores are the only punctuation you can add to a key, right? When you decide to label an object. And it cannot start with a dot, a dash, or an underscore. Maybe it can start with any number or alphabet number you want, right? Values follow the same restrictions, meaning they can only be at most 63 characters long. They have to start out with alphanumerics, but you can add dot, dashes, or underscores as you see fit. Now, labels are strongly used inside of Kubernetes, right? And you can actually use label selectors like does not equal production, like, right? I forget what the two equal signs is. Is it exactly equals? I can't remember now. But usually like equals, the single equal sign suffices, but I can't remember what the double equals is, right? You can also use the n operator like as a set base selector. I'm looking for a role in like these particular keys, right? So like you can actually use like different selectors to find different things. Usually you end up using the most is where it equals or it doesn't equal. I want everything that's not production. I want everything that's not Windows. I want everything that's not, right? Sometimes you match, sometimes you go for the negatives. Just depends. Now, unlike labels, which are pretty much required for you to manage your system, and most of them are generated for you, annotations are also predominantly generated for you. But unlike labels, you can actually associate arbitrary metadata with annotations. So they don't have strict restrictions about like allowed characters and size limits because there's not a lot of parsing done for annotations. With labels, you're going to parse labels to match them against whatever label selectors you're using. Not so much with annotations, right? Annotations are just like, it's like almost like notes that you want to put on an object. You can actually still use annotations to search for certain things, but again, they're very arbitrary. Now, there's a couple of different types of persistent storage inside of Kubernetes. We're going to talk about this in the storage section as well, but just note that there are persistent volumes and persistent volume claims, which is where you claim a persistent volume. There's also this thing called storage classes, which isn't listed here, but storage classes is where the administrator says, hey, you know what? We use NFS here. Hey, you know what? We use EBS volumes from Amazon. Hey, you know what? We use persistent disk from Azure, right? And so you can actually define storage classes that you can actually create static volumes where you can like slice it up and say, look, I made 50 10 gigabyte volumes. Or you can do dynamic volumes and say, look, for storage, whatever they request, they can ask for, and it calls against the storage, and here's the limits for that, right? So just know that storage classes, persistent volumes, and persistent volume claims work together to allow people to dynamically request at the launch of their pod persistent storage. Just to say this, I know this is going to sound weird because people are all like excited about stateful sets as a deployment model. But if you deploy a pod as a deployment, or you deploy a pod as a stateful set, or you deploy a pod as a job or as a daemon set, you can actually attach storage to any of those deployment types. People get confused about this because they're like, well, aren't stateful sets for things that require persistent storage? Yes, but stateful sets are not the only deployment type that can actually have persistent storage attached. The thing that makes stateful sets awesome is that the name doesn't keep randomly changing. Can you imagine if you like were looking up the DNS name for your primary database, they kept rotating every single time? That's what stateful sets are for. So just to make sure that's clear, Stateful sets are not the only ones that can have persistent storage. Any deployment type can have persistent storage attached to it. In addition to persistent storage, which is basically just for a persistent disk, right? You can also, for all of the deployment types to a pod, you can attach secrets, which is sensitive data that can be mounted as a file in the file system that you don't want people to see, but you want the application to have. You can also do what's called config maps. Config maps are cool because like you can literally take an entire configuration file, put it as a config map inside of Kubernetes, and then when that pod boots, when the application boots, and it reads like, so let's say it's http://pd.conf, right? You can actually take that entire configuration file, make it a config map, and when the system boots, it's going to read the config map as if it is that file, which is super cool because you can now specify your config files as objects in Kubernetes, and all the pods, when they boot, will actually get that configuration information. And so you can change it in Kubernetes as a native object as part of your deployment YAML, instead of having to get into the container and specify configuration information, or rebuild the container to specify configuration information. You can actually just do it inside Kubernetes. Outside of persistent storage, and by the way, we're going to dive deeper into all of these. I'm just kind of giving you a preview of the basics here, right? Is that you can set compute resource quotas, you can set storage resource quotas, you can set object counts, but most of the time people don't mess with object counts, just so we're clear. Compute and storage and memory, right, are the ones that mainly get limited, right? By the way, just so you know, when you set like CPU limits inside of Kubernetes, it's done in thousands of a CPU. They call them milli CPUs. So if you say, hey, I want 500 milli CPUs, you're asking for half of a processor. If you say I want 2,000 milli CPUs, you're asking for 2 processors, right? So just be aware, and when we get to that section, you'll actually set some limits yourselves. But like when you get there, you actually can set limits for both CPU, processor, and you can actually set storage quotas as well. Mainly with Kubernetes, you either are going to use the dashboard app, which is actually maintained by the Kubernetes community, or the kubectl CLI, which is also maintained by the community. So just something to be mindful of. You can also, by the way, interface directly with the Kube API if you want to, the K8s API. And there's actually some cool apps that will do that for you as well. Fairwinds is a company that actually administers Kubernetes clusters, in a distributed manner. And there's actually an app I saw Kelsey had posted on Twitter. I don't really post on Twitter. I just read on Twitter. But he posted an infra app, which I'll actually show you later, which gives you a graphical interface for a single cluster. So that was a lot to cover in an hour and 15 minutes. But we basically just ran through the architecture, like the primary nodes, leader nodes of Kubernetes, the worker nodes, also known as nodes inside of Kubernetes, clusters. We talked about the different components, just the controller manager, the scheduler, the kubelet. We're going to dive into some of that in a little bit more detail. We talked about how the pod is the basic unit of deployment inside of Kubernetes and how containers sit inside pods. And basically how pods have different deployment types, such as deployment, stateful set, daemons, and jobs. And when you deploy them, you can attach config maps, which is basically like just key value copies of entire files. You can attach secrets, or you can attach persistent disks to your different deployment types. And we talked about how inside a pod, there's only one application container typically, and just briefly about how you can use kubectl and the dashboard interface to interact with Kubernetes. Whew, that was a lot. We even saw diagrams. We get to talk about pink as a very manly color. So any questions, curiosities, anything anybody wants to review or talk about what we just covered? Okay. So what happens next is we are going to take a break. And since we're on day 2, we're actually going to talk about working with Kubernetes as our next thing. That'll take about 45 minutes, maybe an hour to cover. And so we'll be done just before lunch. And then what will happen is that our labs will actually take about an hour to run. And so we're actually going to we're going to do the first lab before lunch if we can, and then we're going to do the second lab after lunch, both of which will take about half an hour or 45 minutes to run. So that's going to be our afternoon. And then we're going to talk about scheduling next, scheduling and node management, and then we're going to do another lab, and then we're going to do a little precursor on networking. So right now it is 10:18. We've been talking for, I've been talking for a while. You've been listening for a while. So why don't we take the next 20 minutes? So come back at 10:40. It's because it's 10:19 right now. So come back in 21 minutes, 20 minutes technically, and then we will resume the rest of our lecture and then move on to a lab. Okay. See you in a bit. going. So the dashboard basically allows you to do almost everything from a base level that the API does. Know that usually the API has a lot more functionality than the web interface, but you can start jobs, you can stop them, you can turn up the replica set. So if you want to turn up copies, make sure that when you use this, you know what namespace you're in, because you're not seeing objects that you expect to. It's probably because you're in a weird namespace. Remember, namespaces are those virtual slices of a cluster. So make sure you know where you're at. So to understand how the Kubernetes tools function and what they do, remember that when you create a Kubernetes installation, it's a cluster. And the nodes, whether it's a leader node or a worker node, are members of the cluster. The worker nodes or nodes, they run pods. So the pods hold containers, and the containers hold applications. So there's this almost like those little like dolls, those little like where they're nested inside of each other. It's like you've got an application, it's in a container. The container runs in a pod. The pod runs on a node. The node is part of a cluster, right? So just remember that kind of hierarchy, if you will. Deployments are the recommended methodology for deploying workloads on Kubernetes. It's one of the ways that you can deploy a pod, basically. And so once you create a deployment on Kubernetes, what will happen is once you feed the deployment file to Kubernetes, Kubernetes is going to look at its nodes, rank them based on what the pod needs, figure out which of the nodes is most favorable, and it's going to determine which node is the application, the container the pod is going to run on. And then it's going to go tell the kubelet to create the pods on all of the different nodes that are needed. So it's going to check the scheduler every time and schedule pods to run on nodes. And then it's going to just keep going. And if anything fails, if any of the apps actually fail while running, then the deployment will make sure that it enforces whatever the replica set is, right? Whatever the number of replicas. So if there are 5 replicas required, it will keep 5 copies of your app running at all times. Now, when you delete a deployment, you're deleting everything associated with the deployment. So if in the deployment you specified persistent storage, and the policy for the storage is that it can be deleted, then it will be deleted, right? Along with all of the containers and all of the pods specified in that deployment. So remember, a deployment is a type of workload characteristic where you deploy pods that have containers. They may also have other objects in there other than just pods. It might have a service name, for example. And so deployment is that kind of base unit of workload deployment that's usually reserved for stateless apps. But remember, I said you could attach storage to any of these workloads, so you can make them persistent. Here's a very simple deployment command. kubectl create deployment nginx-development. And then notice the image that it's specifying. It's just specifying latest, right? You could also have a deployment YAML file, which has all of your pod specifications, including the number of replicas, which you could also specify on the command line. You could have environment variables, which you could specify, config maps set up. You could have all kinds of stuff in there. And so what could happen is that you can actually get your deployments by using kubectl get deployments. And then if you do a rollout where you upgrade the version or change something about the image, then you can actually see the rollout status as well. And then you can get information in a very broad format if you want it. Also, you can also delete a deployment. Let me see if my file is up. So here we are, and I've got a single node. And notice, by the way, that the data plane and the control plane, it's all stacked on the same thing, right? There's only one node. It's the Minikube node. Note that it's running this version, 1.2.0. So if we ignore the rest of this,
I am going to be typing it out just to remind you, but we could alias that out pretty easily. So here I am getting pods. Notice that there's a BusyBox pod there. There's already an Nginx pod, right? And if we go back, right, we can actually create a deployment just straight up using that same command, right? Sorry. And then if we go back and look at getting in the pods, guess what we see now? We see yet another deployment pod right there. And notice that its current state is that it's currently creating the container. If I keep checking this, oops, it's still actually creating the container, still thinking about it, right? And what might be happening is it might actually be unable to find the container in question. Notice that there are shorthands, by the way, for most of the commands. Like STS will be stateful set, PO will be pod. Let's see, what is the command? I'm going to make this API resources. kubectl API resources will give you a list of all of the objects that you can touch with kubectl. Everything from config maps to nodes, right? See nodes listed right here. See pods listed right here. Notice that there's shorthand names like NO, PO, persistent volumes is PV, stateful sets down here is STS. Just know also it tells you the API version that you are hooking into as well. It'll also tell you whether the object can be actually put into a namespace. By the way, since namespaces are objects, we can actually just do a getctl namespace. We can see all the namespaces that we have, right? And if I want to create one, most of the time it's just using the create command, right? And in this case, just name it, right? I had to. I'm sorry, I couldn't resist. I had to create a Greg namespace. So note here, right? It's just that simple. We got deployments. You can actually use a file to roll a deployment. That -f basically just says read this file. That's what that mainly indicates. We don't really have a rollout, and I'm not going to do it because there's actually a bug where the system will hang on the kubectl side if I actually ask for a rollout where none is happening. If I want to get a deployment and I actually want to see a whole lot more detail, what I can do is I can just get a deployment. Let's say it's the Nginx deployment. Look at that. Tons of information in here just from that simple, like, here's some annotation data. Remember we talked about annotations? Again, it seems like Kubernetes, from my experience, actually uses annotations to hold meaningful data, but it's definitely a metadata. Notice that there are labels here. See this particular label? App equals Nginx deployment. So that way you can find it via the name, which is actually what's happening when I ran this command up here. It's actually looking for where the app equals Nginx deployment. I can also select that in different ways. Notice that here's the name again. Here's the default namespace, because this is where I didn't specify namespace, so this is where it was put. And there's other like strategies, like I have a rolling update, right, where I can only lose a quarter. If I have 4 of them, I can only lose a quarter of them at a time, so this would be 1. And lots of other things like, hey, here's the spec, including, by the way, the Nginx image name that's pulling from hub.docker.com. And then we can look at the status, including last transition time, right? Anything else that's available. Any updated replicas. By the way, this is where the bug is at, is that if for some reason, if this isn't set properly and you do a rollout, like you want to like monitor a rollout, for some reason the command hangs. That was supposed to be fixed. I didn't want to figure it out right now. Okay. So standard deployment commands. This is going to be all over your labs, by the way. So you're definitely going to see this. So how to get a deployment, how to create a deployment, how to delete a deployment, right? And so back to our little piece over here. If we type in gone. If I go and back and get the deployment, it'll say there is no Nginx deployment on the system. If I go back and just say, hey, look, I just want to get deployments. Can you just show me everything that's on here? Notice that the old one is not there. So to update a deployment, by the way, all you need to do is either reapply or change some attribute, for example, right? So you can describe a deployment in detail. You can also undo a rollout. So if you want to roll back one version from something that you've rolled out, you can also just change the image name. So look at this in this particular case, right? You can see that it went from, I'm assuming that's 1.9.1, not a 1.91, but maybe I'm wrong. It should be 1.9.1. So for example, if we go back over here, back to our original deployment kickoff, and let's say I actually do 1.8.7, and I create a deployment, and I'm just gonna keep an eye on it for a second. So currently it says it's not ready. It's probably thinking, I'm not sure what it's thinking about, but it should just retrieve it. Maybe we should create another one with just latest. Oh yeah, let's do another one. I wonder why it's having trouble with Nginx. This is kind of interesting. But my demos have not been going great, actually. Nginx 1 worked fine. Huh. Anyway, well, currently it's not working for some reason. We'll have to troubleshoot that. But basically what this allows you to do is that once it's deployed, it allows you to update the image by just setting the image name to a new image set. What it will do is it will roll the version number of the deployment forward. So just know that it actually does maintain version numbers for deployments. So just something to be aware of. Also, you can actually change and scale your system as well. So if, like, for example, you want to scale to a different replica, you can't, like different size, you can. So in that particular case, and by the way, this whole like deployment version 1 apps, Nginx deployment, you don't need all that. You can just put deployment if you want to. So like, for example, if we were to get Nginx-1, we see that it's pretty standard. And so what we would do is we basically just like run the scale command against the deployment and actually set the replicas. And so what would happen is that now what you're going to see is if I go and get the deployment, what happens is that now it's got 3. But what's happening now is that it should be scaling up. And so you'll see that now it's got 2 running. And if we keep going, now it's got 3 running. So you'll see that Nginx 1 is now scaling up from 3 because I actually set the replicas to that number. If I go back here and change it again to like 5, well, we're going to see the same thing, right? It's going to have 3. We keep watching it, right? Which, by the way, you can set a watch command if you want to. But it just went from 4 to 5, like in a flash, right? And then setting it back down, just that simple, right? Same thing. You just set it back to 1. And what it will do is it will scale in the deployments. It's really just that simple. If you had a load balancer, like a service in front of this system, it'll automatically like register and find those additional replicas with the service if it's like a load balancer, for an example. And so that way things that are hitting the load balancer will automatically get distributed to all 5 of the Nginx servers, or if there's only 1, it will go to 1. So it's relatively nice. Now, you're going to get to run these commands, by the way, in your lab. So you're going to get hands-on with this. When you run pods in default, they're on a private isolated network. So by default, when you run pods, they're on a private isolated network that is cluster wide. And by default, pods are visible from other pods within the cluster. So if another pod needs to get to another pod, they can find each other through service discovery. But pods are not visible outside the cluster. So if someone runs a load balancer outside the cluster and they want to actually talk to you, you can't actually call into the cluster until the cluster exposes the pod in question. And the way you do that is that it's not just the container exposing itself, it's the pod, it's the cluster exposing the pod out to the world, right? And what you do is you add what's called a K8s service in order to do that. Services come in a couple of different flavors. There is the load balancer type. There's the cluster IP type, which means you get a cluster-wide IP address, right, that can go to any node that basically directs the cluster. And then you get node port, and node port binds like to the IP address on every single node, so you can actually hit the port in question and get and actually hit the service. So services are created with the expose command, right? And so in this case, load balancer, by the way, only works if you have set up a load balancer like object inside of your cluster. So like if you're on a cloud provider, you can actually set up a load balancer port. You can also, by the way, run Nginx or F5 or some other load balancer on the cluster, and in default that has your load balancing service as well. But notice it says cluster IP, node port, load balancer, and external name are all options for exposing your different types. Let's take a look at those for just a second. No, not that. Thanks for playing. Let's see. Let's see, Greg, you asked an interesting question. Can you take one node from a cluster and dedicate it to only do load balancing and not run any other pods? You could actually. You could do that. You could like take two like nodes, for example, and set them to be like load balance and only have them run load balancing pods. You could actually make that happen without having. Yeah, I've never done that, but I know you can. I know you could do it actually. So let's look at this for just a second, because I think the documentation is always a great thing to look at. So like here's the service, right? And the selector is against something called my app, and all they're sharing out is TCP 80 and the target port. They're exposing 80 and the target port is 9376, right? So this actually creates a my service with this label. And so it's going to assign what's called a cluster IP address, right? Which is used by the service's proxies, right? There are proxies inside, like the kube proxy, right? Inside all the nodes. And so that way, if it hits one of the systems, it's actually going to go direct it to the box that actually is hosting the pod. So you can reference those in the target port of a service also, as far as like pods have names. You could also just like reference the pod name itself. And so this allows you, by the way, to expose cluster-wide services without having a load balancer. In general, in production, you are only going to run services with load balancers because you need to externalize the hosting of that network traffic and its distribution off of the cluster. In general, you're going to have a load balancer to do that. You can also, by the way, let's see if they have virtual IPs, round robin. Anyway, there's a bunch of stuff here about how kube proxy actually does round backends and stuff, and how it interacts with, for example, with IP tables. So I'm actually going to post this in, but this is how service networking functions for the most part. I'm actually looking for the load balancer piece. Hold on just one second. Multi-port services, DNS, headless, publishing services. Oh, there it is. There's node port. So if you set, by the way, the type to node port instead of using load balancing or instead of using cluster IP, what happens is that it's going to allocate a port from a range specified in whatever range you specify. Like if you say, look, I want you to do 30,000, 30,000, or I want you to do 31,000 and 31,000. If you don't, it actually is going to assign a random port range. And so each node that's going to proxy that application is going to bind that port on the physical host. So if you've got 5 nodes and 3 of them are running the application, the pod, it's going to bind that port on those nodes, right? And so if you want to target the system, you've got to hit that particular port on those nodes to get to the application. That is such an incredible pain, by the way, having to like figure that out and publish it and all those other things. So typically people don't use node port. Plus, if someone else binds the same node port, and you try to schedule your pod on that system, you're going to have port collision, which means your pod isn't going to get scheduled on there. It's really kind of a tough way to do it. It is still recommended that you either use cluster IP or you use load balancer to do it. With the type load balancer, by the way, it actually like hooks into an external device, like an ingress controller, for example, which can be Nginx or F5 or whatever device you want. Notice, by the way, that on like AWS, you can just specify load balancer and the cloud controller manager will actually hook in. They can mix different protocol types. They can do all kinds of stuff, but this is where traffic from an external load balancer is directed at the backend pods. And so the cloud provider decides how it is load balanced. If you run your own ingress controller or your own like Nginx F5 or whatever load balancer you're using, you get to control that behavior, right, as well. So just note, and then external name, I don't know that I've ever used external name. So just scrolling down on this, I'm like looking for external name. I don't know that I've ever used external name ever. But basically what it does is it's not a typical selector, but it basically allows you to map a service to a DNS name. And so then you specify, with the spec.external name parameter, and it says, look, if you're looking for like this, my service, just go to this URL. Oftentimes we use this when we have a resource outside the cluster and we want someone to find it if they get the cluster, and then we want them to go out, like RDS. Like it's an external data source, right? Probably the best way to think about it. Questions there? Oh, did I post that in? Hold on. Let me see if I posted that in chat. Good. All right, so here what we're doing is we're exposing a deployment Nginx server on port 80. And notice if we go and look, this server Nginx deployment is now on a load balancer and it's got port 80, but it's actually talking to 31521 on the system. Where did it get 31521? That's probably where the container is listening on. It's like listening on that particular port. Now, this is something weird, actually, I need to take note of. It says so you can now access the Nginx server using the cluster IP address. Oh, and the randomly assigned port. Yes, you can actually do that. So you could actually take this cluster IP that's listed here, listen to that port, and you actually still would get to the system, but it's also going to give an external IP address, or you could use this IP address on port 80, and it would also lead right into the system as well. So do note that it still actually does some level of cluster binding on the system, like a cluster port, but when you externalize to a load balancer, it's actually hitting a cluster IP and then getting redistributed. Cluster IPs are typically like on the back end, still doing all the magic. And then, by the way, if you're running Minikube, you can actually just name the service, and it will actually give you the IP address and port that it's using. So we're going to be doing some that sounds really odd. I apologize. We're going to be typing some expose commands actually in the labs. So you will basically get a chance to expose your services. Okay. Namespaces are slices of the cluster. We talked about that before, right? These are slices of a cluster. Assets by default are initially created in the default namespace. New namespaces, as you saw before, where I made a Greg namespace, are just like basically, again, put the object, namespace in this case, then the name, and that's it. You can create anything through a YAML file, by the way, and that's actually the recommended method is that you actually create things through YAML files and not necessarily using the command line. Because these YAML files, by the way, can then be checked into a repository, right? So it's infrastructure as code at that point in time. You can get pods. Note that if you don't specify a namespace or specify like a -a, it's going to default to the default namespace typically, or whatever your default namespace is. Labels, just as a deeper dive from what we touched on before. This is where you can get nodes and you can show all the labels on a node. So for example, if we go over to us, notice all the labels that are here, right? Just maybe that'd be better actually at the top. Let's do that again. Notice here that it's listing architecture. It's listing operating system by default, right? It's listing the host name. So there are actually some labels that are created for you, right? And they're under different things. So like beta.kubernetes.io is a different prefix than kubernetes.io, even though they both have OS Linux, right? Notice that this says minikubes.k.io. Here's the commit version, so you can actually find the commit revision for Minikube. You can find the updated at time for Minikube. You can find the version of Minikube, which I find fascinating because it's actually running 1.20. So that's a little, maybe I haven't updated the software in a minute, right? So know that there are labels that are actually created for you. You can list all the nodes with a label, for example. You can label nodes like this. In this case, they're doing workload equals prod. You can overwrite an existing label. So we change workload equal to staging. And you could remove the node label by providing the key without any value. Now, I'm going to show you one of the worst command line flags I've ever seen in my entire career. And it shows up here, and it shows up on scheduling, not scheduling, taints and tolerations, which is something we're going to talk about as well. I want you to know that this little dash after this little workload is not a mistake. It's actually how you remove the node label. Like you can remove the key. I got to tell you, that is one of the worst things I've ever seen used as a command line parameter. No dash delete, no delete, no like nothing. It's literally you put a dash after the key value. They do that again with taints and tolerations. I can't even tell you. I don't even know. I have literally sat with Kubernetes captains and said, this is the worst. You need to change this. And they're like, what? It's just a dash after it, right? Yeah. I mean, I got to tell you, Greg, even minus would be better, right? Because at least it would stand out more, because most people think that's a mistake, right? Are there supposed to be a dash after that? No, the dash is important, actually. So anyway, I'm off my soapbox now. So moving on to annotations. Annotations are the same thing, right? Just they're not like you use like label selectors in order to do management per se. You can actually do management with annotations. So, you know, here, by the way, if you want, you can actually add your own annotations to the system. It works remarkably like labels. It's just annotation, right? Yeah, that's weird. We don't have any commands in there. I guess because annotations are very arbitrary, we don't typically use them, right? Here's some other useful commands. Get is your friend. You want to get nodes, you get nodes. You want to get pods, you get pods. You want to get deployments, you get deployments. You want to get stateful sets, just type in stateful sets. You want namespaces, get namespaces. You want persistent volumes, get persistent volumes. You want storage classes. I mean, everything is listed. Get is your incredible friend if you're touching Kubernetes. Now, just like we have Docker exec, right? Because you can create your own deployment, right? Just instantly to run an image. Docker exec will allow you to interactively come in to a particular pod. And by the way, if you put a -c and then a container, you can actually get to a specific container in the pod. And so like here, this is opening a bash shell against the Nginx web. And so here, if we go back, if I go out back here and I actually get my pods, and remember, just to say this, see that whole random number that's at the end of that? That's totally random. So even though this is an example, that's actually not like, it's different every single time, right? So in this particular case, I have Nginx up here. So let's just say that I want to copy this. Oh, really? Weird, all these different terminals. You're not going to let me paste? Seriously? Huh. Shift insert usually gets it done. And wow, you're not going to do that. Okay, fine. I'll just type it out. That doesn't bother me. All right, sorry. You need to watch me like type this out slowly. C49886-JGVH6 bin bash. Oops, don't have a dash on IT, so that's going to cause a problem. Now remember, because I'm in get bash, I've been having trouble with this particular piece. But what that would do is that would open up bash inside the system. I had to switch to another system, so I don't have Ubuntu running over here just yet, but I'll fix it. So that will allow you to bash into the system, and basically then you could troubleshoot all you wanted to inside the container, right? So that will allow you to do what you need to do. Also, logs will actually get you logs about the container in question. So just so you know, this only works if you are actually writing your logs to standard error and standard out. Otherwise, if you are using some other mechanism to export logs, it'll only do this if it's actually being captured by standard error and standard out. So if you're writing externally directly from your application to another system, you won't see any logs because Kubernetes is not managing the logs for you, right? So just know that the logs command only works if Kubernetes is actually capturing log data for you. If it's not, then you won't see it. So here it's just like showing me the Docker entry point. Here I was looking for shell scripts, Docker entry point.d, which by the way, you could copy shell scripts into Docker entry point.d, and so it would actually load them as part of the Docker entry point script. And then it looks like it's getting a checksum of the Nginx conf, and then enabling listening on IPv6 for the conf, which is kind of cool actually. And then you can copy files in to the system, which is very like the same as the Docker copy command that we were looking at earlier. So there's a lot of similarities there. Get a list of pods. Sorry, you can get everything. Sorry, that was a repeat slide. So that was chapter 6. Like that was us covering everything related to like brief installation from a client side, but also understanding like the server side of things. Remember, Kubernetes the hard way is your friend if you really want to master operations and installation of a Kubernetes cluster. We talked about deployments and the different like just general things to consider with deployments, how to use YAML files, right, for deployments. We talked about networking, services when you need to expose stuff out across the cluster, slicing up the cluster with namespaces, which allows you to run different pods in different namespaces. So you can isolate them away from each other. Just some bevy of useful commands. We didn't really talk about scheduling and node management because it actually comes later on. So I think those are accidentally left in here. But just note that when you set up a bunch of pods, they are scheduled one at a time very quickly. Questions, comments, soliloquies? Uh-oh. I actually have heard of Lens. I haven't used it a whole lot. It's been recommended that I do use it. I mainly use Fairwinds as my favorite kind of app for managing Kubernetes clusters, but I hear Lens is really good for offering insight and observability into a K8s cluster as well. Oh, last time I thought it was a different URL actually. Kate's Lens. Yeah, that's pretty slick. Fairwinds also has a really great, so does infra.app. They have a pretty good one as well. But I hear a lot of good things about Lens, the Kubernetes IDE. Oh, cool. That's cool, Greg. You actually wrote an extension for Lens. What was the purpose of the extension? Iframe of web content, like a dashboard. Oh, that looks good. Huh. Thanks for sharing that. Let's take a look at this. Written in Go, no less. Perfect. All right. Does anyone have any questions before we dive into the various types of deployments that we have? Oh, well, that makes sense. No? Okay. Okay. So I talked about this before, because now we're on this new chapter, and this will be the last thing we cover before we take lunch, is that your way of deploying pods is in workloads. That's how like pods get deployed, containers get deployed. That either happens through a deployment, a stateful set, a job, also known as a cron job, or a daemon set. Now, some of the workloads are better suited for different types of applications. They are for different purposes. Like jobs, or really like batch jobs, are really just for these one-off kind of things that you run small but repeatedly. They're not really for hosting applications per se. And then if you want to run a database application, which is stateful, versus an Nginx web server, which actually may have very little state on it at all, those require different workloads, typically, depending on what you're trying to solve for. And then, of course, if it's more operational and needs to be associated with every node, then that's where daemon sets come in. So let's talk about these. Whew, that is an eye chart. All right. So let's take a look at this thing. So over here, we've got a bunch of nodes. That's cool. And this is for a daemon set. Oh, I see. So for a daemon set, what happens is that you've got a bunch of, like, you've got these pods running right here, and there's one on each node. If it's just part of a standard deployment, it'll have a replica set associated with it. And a standard deployment might actually stack multiple nodes if necessary, but typically it wouldn't do that. This pod actually would be running over here. It would typically like distribute them typically pretty widely. It just depends. Maybe this node doesn't actually have any memory available, and so therefore it might run these two. You can actually set what they call affinities and anti-affinity to force pods to run on systems or not run on systems. Or you can actually set anti-affinity for them against each other, so they're like distributed more widely. But that's a deployment. With the daemon set, it's actually running one per particular node, which is good. And then with a job, what ends up happening is that the job, like jobs are just queued, and they're just run again and again and again. And a cron job runs off of time, and a job is like parallelized, right? So a cron job is like typically a single job just run off a time-based reaction. And a job is where you want something to run, like let's say you're calculating pi and you want to do portions of it out to a certain number, you just kick that job out to where, you know, you're going to run this 10, you're going to run this 10, you're going to run this 10, like calculate out to this like far, right? As an example. So batch processing works really well with jobs, but also, you know, a lot of people can find like where they run like standard kind of like deployments for them as well. It just depends. But cron jobs are time-based, jobs are parallelized or distributed, like, you know, concurrently. And then daemon sets are associated with single nodes in a cluster. Let's talk about that in a little bit more detail. So you can manage workloads in three ways. You can basically use the kubectl command. That's basically what it is. You basically run it, you create it, run it, expose it. You can scale it or auto scale it, right? As needed. So those are imperative commands. which is like very verb driven and command line driven. You can also configure objects, right? Using configuration files, in this case, YAML. You can use JSON. There are tons of references for this. Like if you're looking for like generated. Interesting. That link doesn't even work. Let me take a quick note. We'll have to fix that. There are references for the generated APIs. Let's actually go and take a look ourselves. What if that was just a requirement stock, actually? Come back. So here's the reference stocks for the API. I'm not actually sure what they were trying to show here, honestly. Oh, for the imperative object configuration. Gotcha. Yeah. So there are actually, almost with the Kubernetes documentation, there are tons of examples. So for example, if we come out here and we're like, hey, I really would like to learn how to mess with stateful sets. What will happen is if you come to stateful sets, you will actually see tons of like YAML, as we saw before, that will actually walk you through how to create like most of the configurations that you're going to see, right? And you'll notice this one, for example, has a storage class definition with a volume claim template. And then it's actually using Nginx, a slim version of it, to generate a container. And then it also is like linking up to a service name. This is a stateful set for the service name. So this will be Nginx 1, Nginx 2, for example, right? This has a certain number of replicas to it. So notice that there's a service link as well. There's a stateful set, and that has a volume claim template in it as well. So this is all you need, like basically, to run a stateful set with a service associated with it. So there's tons of examples throughout the Kubernetes documentation for anything that you're looking for. So if we switch over to daemon sets, you'll see like a daemon set documentation. If we're looking at jobs, right? Here's an example job. Oh, that's funny. Here it looks like they're basically calculating pi, right? Out to 2,000 digits. Oh my gosh, I haven't run Perl like that in a long time. And then there's also cron jobs. This is time-based. Notice this has a schedule attached to it, right? So out here on the Kubernetes documentation, there's tons of example Kubernetes. There's YAML files. There's also tons out there on GitHub as well. Please, 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 if you grab it from somewhere other than the official source, make sure you know what it's doing. If it has something weird like this inside of it, make sure you know exactly what kind of shell it's executing and what it's doing. It's not that the majority of people are not out there to hurt you, but you never know what you're going to get. Declarative operations, by the way, require you to basically say, this is what I want. I don't really care how you get there, right? And so it's not step by step. It basically says, look, I want 3 replicas and I want based on this image. That is the majority of the YAML files that you're going to find is they're declarative. They say, look, this is what I want the end state to be. I want this image with this volume attached with this many replicas. And so everything that we just looked at is actually declarative object configuration. It says, this is what I want the end state to look like. It's not procedural or imperative where it says, first do this, then do this, then do this, and then do this. So Kubernetes uses declarative object configuration for most of its declarations. And sorry, I realize I might have, they do have imperative capability, but most of the time we use declarative as our object configuration state. Now, when you set up a configuration file, as we could go back and look at, notice the first thing it does is it says, this is the API version that I want to connect to for a cron job. Now, most of the time, you're going to grab somebody else's YAML file and modify it. But here's a little bonus question. If you needed to discover what the API version was for a cron job object, who remembers the command that I ran to list all of the objects inside of Kubernetes? It's one of those important commands, by the way. It shows up on the any of the Kubernetes exams. So remember? I know I'm throwing a lot at you. So kubectl API resources is going to list all of the objects. And if we scroll up to jobs, so here's jobs down here, right? See how this says batch version 1? Batch version 1, right? If you need to specify the kind, notice how over here it says job. Like, so even though the object name is listed as jobs, it's listed as job inside the kind. Let's go look at that. Well, this is a cron job actually. So let's go back. So cron job batch version 1. Notice it says batch version 1 and then it has a beta 1 attached to it, right? Which is interesting because it's not in beta anymore. So I wonder why it's still listing that. That's funny. And then notice over here, it's cron job, right? Not cron jobs. It's cron job. So then that's what you would list for the API version. I bet you, by the way, since it's very much backward compatible, I bet you if you put that in there, it will work just fine, right? So batch version 1, cron job, and then the rest of this, as far as like metadata and the specifications, you would have to look this up in the documentation to know exactly what to put here or what you could put here. So you might come in here and say, look, what if I just want to like have a template for the containers? What if I want to add something else? What if I want to add a service name, or if I want to link in a persistent volume claim? Where would I look that up for? So just remember, kubectl API-resources will get you not only the short names, which by the way is incredibly important for the certified Kubernetes administrator exam or any of those associated exams, because that's a very intense time-based exam, but it's also just good in general for you to know where to find the API versions and whether or not it can be namespaced and what the kind name is. Let's go look at namespaces just in the documentation really quick, just to compare. So you can actually create your own namespace. Oof, there's no example here. Let's pick something else. I don't want to have to write my own here. Let's do secrets. Surely secrets has examples, right? Different types of secrets are listed here. Here, for example, you've got the API version to 1. Kind is set to secret. Let's go take a look. Secrets, version 1. Kind is set to secret. So again, just know that if you need to find that information, API-resources is where you find it at. Good. So inside the file, you'll find the API version, which we just tracked. You'll find the kind, which we just tracked. Metadata, which is usually information about the kind, like the name, for example, that you want to like put, right? That must be unique for the object. But you can't have 2 deployments named Nginx-1. They have to be unique. Now, the pods underneath that deployment are going to get their own unique names. But when you create objects, you have to manually specify the name. Object specification is listed under spec. If there's replicas, it's under replicas. If it's templates, it's used by all the pods, for example, such as labeling, images, resource limits, for example, will also be underneath there. Any volume mounts. So that's usually the configuration file schema. Now, when we're looking at the APIs, by the way, you saw that there were betas. There's like version 1, there's that's version 1. Again, there's version 1. There's actually a bunch of others, possible ones, right? Depending on whether you're using like validating webhooks or custom resource definitions, which I talked about before. But usually version 1 and apps 1 will cover most of what you're doing. But notice if you're using cron jobs, you're gonna have to look at batch version 1. And so you do actually want to have to come in here and look. If you're setting up storage classes or whatnot, using a storage driver, role-based authentication is going to use RBAC. If you're setting up policies like pod security policies, or disruption, but like you just have to come here and look. That's the bottom line. Wow, they just kind of keep going. It's a lot. So again, kubectl API resources is your friend. This will help you find the API resources that you're looking for. We've already shown that. Good. Before I move on to stateless applications, any questions about that whole general statement about creating YAML files, the fact that they're going to have like metadata and specifications and templates inside of them? I don't expect you to have that memorized, but any questions or curiosities there? Okay. Okay. So remember, a stateless application is not going to be persistent, right? So any data that's inside the container is going to get deleted as soon as the container is destroyed, right? So Nginx, basically, Java application servers like Tomcat can also act as web servers. You basically are going to be using deployments for those. You can make deployments persistent. Remember, you can attach volumes to practically anything. But remember, the names are not unique. They're not going to preserve state. So just know that if you're running stateless, you're typically going to be looking at deployments as your primary medium. Here's a sample example. Notice the kind up here is a deployment. Here's the only metadata, which is basically just a name. Here's the number of copies. They have a label. And then this is just running this specific image, 1.10. Oh, I was wondering where that was. The container port's listening on port 80, right? Because basically what you're specifying here is that the application is listening on port 80. So tell me what port the container is I'm supposed to connect to on the container. It's like we're on 80 because that's what it's listening to by default. Deployments, as we saw before, is you just get deployments. You can describe deployments. You can get the pods inside of a deployment. You can describe the pods inside of a deployment. You can roll out a new version by updating either the image name or changing the replicas, number of replicas. You can scale it, right? You can delete a deployment by running delete. You saw me do all of that earlier. So that's for deployments. And then if we want stateful applications, you want to have a consistent host name that persists no matter how many times the pod is restarted or if it's moved even, right? And so they have unique identifiers that are maintained in an ordered, safe way. So your first instance of a stateful set is, usually -0. The next one is -1. The next one is -2, and so on and so forth. And as that pod basically restarts, it keeps -0. So the first pod, as it's restarted, keeps -0 and is restarted with like MySQL -0 as an example. Here's a sample file. Notice the kind is set to stateful set. It's got 3 replicas, a rolling update strategy. A lot of this is left blank, but like you can kind of like get the idea is that it is mounting a volume. It is claiming a particular volume, and it's going to grab disks that are only going to be used once. You can only read write them one time, right? By this particular container. So it can't be reused. Nothing else can grab it, right? It's going to be 1 gig in size, which I don't know what this is running, but that seems kind of tiny. This is just listing what those gaps are as far as port name and PVC name and whatnot, right? When you work with stateful sets, same thing applies. You just kubectl apply and then the file to create the object. And then you can get stateful set information about the stateful set based on its name. You can describe it. You can get the persistent volume claim. Now it's associating persistent volume claims here because typically you run persistent volumes with stateful sets because of their persistence in naming, right? But you can also just get pods. You can do rollouts. You can scale them the same way. You can delete them the same way. The only difference is that you're going to put a stateful set and a stateful set name in the commands. Otherwise, you manage these just like deployments. And the only other thing that's here is that you're probably going to have a persistent volume claim and a storage class, most likely with a stateful set. I don't know that I've seen anybody run a stateful set without associated storage. So just make sure before we move on, stateful sets are for stateful applications. Deployments are for stateless applications. The only difference between the two is the persistence of naming identity on the stateful set side. They can both have attached storage, okay? Last is jobs. Jobs represent finite, meaning like perpetual applications that are independent and often want to parallelize tasks to run to their completion. This could be like, rendering video, batch processing, reports, it could be genomic data, it could be all kinds of stuff, right? And so you can create a Kubernetes job to execute and manage a batch task on your cluster, right? And then you can specify the maximum number of pods that should complete their tasks before the job is complete, as well as the maximum number of concurrently parallel running pods that you want at any given time. Here's a sample, right? Oh, it's actually showing this, the Perl example, right? Which in this case, you can actually run up to 5 parallel pods at a time. It has 100 seconds to run, and all you really need is one completion, which is interesting. I probably would have set that up in some kind of range, right? That said, hey, if you're the first one, do this. If you're the second one, run this range. Third one, do this range. But, whichever. It's optional, but like when a job completes after like first run, it can stop. But like let's say that you only needed to run like 10 times because you've got like 10 batches, right? Then you can do it that way. Active deadline is like, otherwise, if something gets hung and you don't have an active deadline, it will just hang there indefinitely. You'll have to go manually troubleshoot it. And then parallelism is just multiple concurrent jobs running at the same time. So this really is for batch jobs, is what this is for. Same thing. Exact same thing. Works exactly like deployments, exactly like stateful sets. The only difference is those options for running in parallel, and for completion, and for active deadline timeout. That's it. Cron jobs work the same way. Wait, hold on. Do we have cron jobs in here? Let me just check. Oh, there's no cron jobs in here. Cron jobs work the same way, by the way, as batch jobs. The only difference is there's a schedule parameter that you say how frequently and repetitively you want the cron job to run. By the way, I'm assuming everyone knows what cron is on a Linux operating system. You've used cron in some form or fashion. Is there anybody who doesn't know what cron is? So, and there are cron generators, by the way. But basically you can say, look, I want something to run every 6 hours as an example, every minute, and I want it to do it every 10 days, and I only want it to do Monday through Fridays, and I want it to do it every 4 months, right? And like, let's say the command to execute is, bin, I don't know, calce, right? And you don't necessarily want to handle execution output. You can just generate a cron tab. And what this will do is this will show you this kind of interesting, these fields right here are actually the cron tab. Now notice here that it's actually running bin calce, but like, this is like, wait, what? Every 6 hours, every 10 days, every 4 months, and I only want you to do it Monday through Friday. Isn't that weird? This first field right here, let me blow this up because this probably looks like an eye chart. This first field right here is minute. This is hour divided by 6. This is days. This is, months, I think, if I remember correctly. And then this is Monday through Friday. This is days of the week. Which days of the week is it going to run on? And then after this, it just is running the command, and it's actually redirecting, right, the standard error and standard out. So cron dabs are what Linux admins and Unix admins have used for years, decades, to run repeatable time-based jobs. So just know that with jobs, there's also cron jobs, right? And that's just a time-based delineation of a job. Yes, John, that's exactly right. Not so much the triggers and variables, but you're defining the schedule. Actually, I guess that's a trigger. So you're right. You're defining the schedule trigger by which your job is going to run, right? You're saying, look, I want my Lambda function to run, this frequency and interval. It's the same thing. You're just specifying when you want this job to run. Usually it's a consistent time, right? That's it. And then the last thing, which is probably the easiest one, is daemon sets. So if deployments are for stateless applications, stateful sets are for stateful applications. Again, remember, the naming is the only distinction between those two. Storage, it can be attached to any of these jobs. Then you've got jobs, which are batch jobs. Then you've got cron jobs, which are time-based jobs, but are not batch. They're not parallel. They're not running in parallel. Cron jobs typically run single execution. And then you've got daemon sets, and daemon sets just run on every node in the cluster. So this is where things like log collectors like FluentD, monitoring services like Prometheus agents, Datadog agents, that kind of thing. So you create it and deploy it on the cluster, and it'll actually make sure there's one per node. So every single node will actually end up with a daemon set. Here's an example, and notice again that the kind is set to daemon set, right? You got a spec, the app is a daemon set example. Here's the name. The image is actually Ubuntu Trusty, and it's actually running basically an echo command every 10 seconds. Hey, I'm running on this host name. Hey, I'm running on this host name, right? And so it actually, if you go look cluster wide, it would show you like what host name it's on, right? This would probably be more likely like a FluentD container or a Logstash container or a Prometheus agent container or a Datadog container, not just some random echo command. Okay, so those are the different workloads. There's 5. Deployments, stateful sets, jobs, also known as batch jobs, and then cron jobs, right? And then we've got daemon sets. Those are the 5 workload types that you can run. And you can, by the way, can add a custom resource definition if you want to add your own workload, like your own workload type. You can do that as well, right? So you can actually extend Kubernetes the way you want to. Okay. You can do rolling updates on all these workloads, right? So daemon sets, deployment, stateful sets, right? They can all be updated. Typically, with batch jobs and with cron jobs, you can update those as well, but that just means that next run, they're going to update, right? Because if they're in the middle of a job, they're not going to update while they're in the middle of a job. Because remember, they don't run persistently. Only daemon sets, deployments, and stateful sets run persistently, right? So just be aware. Now, if you set it change an image or set a resource change, that will like, I don't know if I don't think resource limits actually trigger a change. At least it's never triggered a change. It's never triggered a new version for me, right? But an object changing the image will definitely do it. And you can check the rollout status by just saying, look, I want to like rollout status. If you run into a problem, you can pause it. Oh, guess what? The internet's down. Let's pause it for a second, right? And then you can resume it when you're done. That can all happen. You can actually look at the history of a deployment. You can roll out a specific revision. Like, if you want to see a specific revision, you can also roll out a specific revision as well. Like, you're like, look, I want you to roll back to this previous revision. So know that the history command can show you the revisions. You can then ask to see a specific revision, and then you can roll your system back to a specific revision as well. So that's the great thing about immutable infrastructure, and that it will work unless somehow the image that you're referring to, if it changed some specification, doesn't exist anymore. But I mean, 3 revisions back, you'll probably have that. And that's it. That's the whole thing. We just covered the 5 types of workloads, a general smattering of all the commands that you can run to explore those workloads. Any questions?
I have one. I don't need like super specifics on this, but just trying to wrap my head around like when you're doing the revisions. Is the life cycle kind of like the load balancer will direct traffic away from like the first one we're going to update and then re-provision that and then start driving new traffic there? Like on a very like broad overreaching level, I don't need technical details, but how do those when we're switching up the versions, like what's that process look like?
Yeah, so and that will vary depending on your update strategy. So there's an update strategy that you get to I'm over here doing my own thing. That you get to set on basically your particular workload, for example. And so rolling update, for example, is where you have an update strategy like set up. You can actually specify different like update strategies as you want to, right? So notice this set up here. So a rolling update will typically take one out of service and then it will like update it and then put it back in service. So it'll actually rotate through the setups. When the container is taken out, the load balancer will typically like not send traffic to it, right? Now, if it's in the middle of a session and you haven't put like something in there like connection draining, right? Then you can disrupt a user session, but that is very dependent on the load balancer. So like the AWS and Azure and GCE load balancers, you can actually set them to say, look, don't deregister the system until the session is finished. And so Kubernetes will actually work with the load balancer to make that work because it'll ask the load balancer to deregister the system and then it will update it. And so the behavior also varies by load balancer, but for the most part, the load balancer is going to take that container out of the pod out of service, and then Kubernetes will do the update, load the new pod up, and then re-register it with the load balancer. That's the general behavior. To help?
Oh yeah.
Good. Now I'm wondering why I'm not getting, well, that was a disaster, whatever Michael Forrester just decided to paste inside. I wonder why I'm not getting the update strategy linkage. That's a little strange. Hold on one second. Wow, that's a really horrible search. I'm sorry, I'm being sassy. That's so weird that they would not actually give you the update strategy as the first one. When I just did this 2 weeks ago, that was the first thing coming up. Huh. I will have to dig up, but there's different deployment strategies that you can follow. There's rolling update. There's all at once. They don't have a blue-green, but they do have a cutover. I can't remember what they call it. Usually most people do rolling updates because it's just like when you have an intelligent load balancer, it handles all that for you. The customer doesn't see it. I will dig that up and make sure I have it by the time we get back from lunch. Okay. We are going to talk about scheduling next, but guess what? It's 11:56. So when you come back from lunch, we're going to work on some labs, and we actually have a lab about accessing the Kubernetes API, and we have a whole lab set about managing workloads with Kubernetes. So that's what we're going to do when we return, is that we're actually going to work on labs 7 and 8. I know that some of you have done lab 7. And as usual, before we go, it is worth mentioning that Kata Coda does actually have a whole section on Kubernetes. It's pretty simplistic, but it's pretty diverse in terms of the topics it covers, right? So if you want to pop into serverless or networking or observability fundamentals, there's a bunch of stuff out here. So just know that there's a lot. And remember, there are scenarios inside some of these courses. So it's more than just like one little set. So like if you were over here and you wanted to like get a different perspective on the Kubernetes fundamentals, or you wanted to add a cluster with kubadmin, you want to deploy a simple application, these are all here. I highly recommend that if you do finish a lab early, or even just wanted to like reinforce some of the concepts, to come in here to Kata Coda, to the Kubernetes section and just dive in, because it's Totally worth it. I also do want to mention that both Docker and Kubernetes inside Katacoda has a playground where you can just get access to a cluster. So let's say that you don't have one running locally and you just want to be able to play and kick the tires on something, or you want to do something that you know is destructive, right? Or you're not really sure what the impact is. You can actually get in here to the playground with 2 terminals, both on a worker node and on a primary or leader node, and like do things like run cluster info, for example, right? Oh, wait, hold on. We got to launch the cluster first, right? So yeah, so just know that this is here. Okay. Any questions before we break? Okay. It is 11:58 by my watch. We are going to be returning at 1 p.m. today. So that will be from my watch 62 minutes for those of you who are potentially in other time zones. But in 62 minutes, we're going to come back. So go have lunch, go take a break, go take a walk, grab some water, get some food, and we will see you back in 62 minutes. Okay. See you in a bit. I recording right now? All right. So, so switching off of labels. Labels are coded. You put them against the system, and then you have to match them. So that's a different thing, right? So you're matching labels or moving away from labels. Affinity and anti-affinity is a little different. So they can represent more complex logical expressions. So like you can do like conditionals if you want to, whereas labels are pretty much like, do you have this? I want it. Are you this? I don't want it. Right? Or I want, you know, this in, you know, this set of information. So you can like match a role where it's like web server, database server, for example, has from the example we saw earlier. So you can actually match a list, if you will, an array. But node affinity, anti-affinity is interesting because it can basically say, look, it can be either this label or this label, right? So it's not necessarily a list. You can actually do conditionals, or you can say, look, I will do it if this label is this, but not if this label is this, right? So you can actually set like resistances and whatnot. I have to say, I haven't really used affinity a whole lot or anti-affinity because honestly, with labels, I tend to be able to figure everything out. It's definitely a more complicated structure, but you know, I hear from like Kelsey and other guys that it's like more flexible if you want to express more complicated scheduling priorities. But like, even when I pinned Kelsey down about it, I was like, hey man, like, do you really need this? He was like, you can figure ways around it, but there probably are use cases where you can only use affinity, right? He says, besides, get good at the stuff that nobody uses. I was like, go away. Anyway, it does have more operators in it, such as like, you know, role in like this set or not in this set, or does the label exist? Does it not exist? Is it greater than this number or less than this number? I could see value in that if you were tracking against like resource consumption, like, but then you'd have to dynamically change the like label, for example. Anyway, there is a way better set of examples if we go and look at affinity. For example, if you want to assign pods to nodes using affinity. So for example, notice that this is required during, oh, actually, that's probably an eye chart. Hold on, let me blow that up. So here like is a pod specification for Nginx, right? And it actually has a spec for affinity in it, right? Which is different, right? Because you need to show like you have a bunch of labels here. By the way, let's say the disk type is SSD. And so you're going to verify that the label is set. And so in this particular case, what they're doing is that because that label is set, they're like, look, I want you to schedule required during scheduling. I will only actually do, you can only schedule this if the disk type is set to SSD. Now, I just want to say this, ladies and gentlemen, everybody, if you're not running SSDs on your production systems, please talk to me because we need to talk because SSDs are the bomb. And once you have SSDs, you can't go back to mechanical hard drives. Will you ever go back to a mechanical hard drive in your laptop? Then why wouldn't you do the same thing for your servers? Regardless, I digress. So this is how, by the way, you would set up node affinity. And notice that there's a policy here that says, look, it's required during scheduling, but if somehow this label gets removed during the actual execution, meaning the pod is actually on there, it's not going to evacuate the pod. Let me say that again to make sure that you're following me. You got a bunch of nodes. The disk type is set to SSD. You go to schedule a pod to run on those nodes and everything's cool. But then a junior dev comes along and accidentally removes the label off those nodes. If you didn't say ignore this during execution, when that dev took the SSD label off the nodes, all of those pods would evacuate off of that node. So this gives you the flexibility of changing the labels without wrecking your deployed pods, right? There's nothing wrong with like moving pods around, but it can cause load on a Kubernetes cluster. So you want to be judicious about that, right? Okay. So here you just apply it in this particular question. And notice that this was required node affinity. There's also preferred node affinity, which says, look, I would prefer this during scheduling. Please ignore it during execution. I'm not going to get upset if you don't have it, but if it's available, I would prefer that we use this. That was a lot of verbiage, wasn't it? You know, computers don't say that. So basically what it says is, look, if you have one available and it's in the list, let's just use one with an SSD on it. If it's not present, like you don't have one that has this label, it's still going to schedule it. It's just preferred that it has the SSD. If it doesn't have it, it's still going to actually deploy the pod. Do you see how that's a more complex conditional than a label? A label's like, do you have it or do you not have it? Because if you do, great. If you don't, I'm not scheduling. Remember, labels are hard stops, right? By the way, just to say this, I tend to be hard stop on my things, which is probably why I end up using labels, because I'm like, look, if it doesn't have GPUs, then don't schedule this machine learning thing. You're not going into Gen Pop with your machine learning training models, right? You need to stay in the specialized servers. So this is probably why I don't use Affinity a whole lot, because I tend to be pretty black and white, or like hard about my boundaries around these kind of things. But just know that you can prefer things during scheduling. You can also say like required during scheduling and required during execution as well. So there's different affinity policies that you can set with Affinity. Make sense? That's just a sampling of the complexity. This is kind of a general kind of pseudocode statement that says, hey, I would like to, this is required during scheduling, but again, ignored during execution. Says, look, I'm looking for the key where this is the label and I want it to have either of these values. If it has either of these values, then I'll go, right? So this is an either or statement. Here's an anti-affinity example where basically you're putting a negative which says not in. Like I don't want you to schedule, right? I want you to schedule where label 1 equals value A, but I don't want you to schedule where label 2 does not equal C, right? So as long as it's not, label C is not equal to this, then you can go ahead and come on in here. So just remember that there isn't like an anti-affinity statement. It's a negative against the evaluation. Notice that the spec says affinity and then note affinity. It's not anti-affinity. It just means that here you can set anti-affinity and say, I don't want these, right? In this particular specification, not in. Okay. Very simple, but gives you a taste of affinity and anti-affinity. How can you use like complex conditionals to attract towards a certain set of labels or repulse against a certain set of labels, and you can combine them, okay? Questions or considerations before we move on to taints? Oh, we're doing good, actually. Obligatory coffee or tea break. Well, actually, this is coffee. Don't usually drink coffee. Let's see. So if node affinity is a property of pods, which basically attracts them to the labels that are put on nodes. By the way, the labels don't just have to be nodes. You can actually, it's mainly nodes, but you can actually put it on other things if you want, like disk drives. Like volumes, for example. Taints and tolerations, so just be clear, taints are about nodes. Tolerations are about pods. I don't know if they say that. Yeah, tolerations are applied to pods. There it is. It says at the bottom. So taints are applied to nodes. Tolerations are applied to pods. What that means is that when you taint a node, you can taint, which is, I gotta say, is a little weird because you can taint a node and say, look, don't schedule against this node at all. But if there's things running on it, you can keep them running, right? So there's like 4 different levels, if you will. Let's talk about taints. So you can add a taint to a node by using kubectl taint, much like kubectl label, right? Again, nodes primarily. You can actually use the following effects against a key value store, which is like, I don't want you to schedule anything here. I would prefer that you not schedule anything here, which I got to tell you is really strange. It's a strange value. And then you can say, look, nothing can execute here, right? So no schedule and no execute make perfect sense to me. But I'm like, why would you prefer? It's like, oh, I have a node that's kind of flaky. It might be failing. I would prefer that you not schedule it here. That's weird to me, right? Hey, Al, pay attention to me. Sorry, I have a 360-degree camera and it likes to talk to the screen. They have some kind of like thing going on. So sometimes it pivots off of me. So, hi, can we make me primary? Anyway, so so prefer no schedule doesn't make any sense to me, honestly, because I wouldn't use that. But if you want me to clear everything off of a node, I will taint it no execute, and then the Kubernetes will slowly move everything off of the node in question. Like if I know something's failing, I can just taint it and say, look, no execute on this node, right? You can also coordinate it off, which that's a whole separate thing. But I can taint it and everything will get moved off of it. You can also say, look, I'm working on this system. So like, let's say you evacuate everything off of it and you would say, and I don't want anything new coming in here as well. So don't even try. You can actually put no schedule, right? And no execute on the system, like separate, like key value labels, but different effects. And then that way it won't schedule anything, won't even attempt to schedule anything, won't even talk to the system to schedule, and it won't run anything either. So anything that's running will come off of it. But prefer no schedule, I have to say I've never used, right? Note that this has the greatest command line parameter you've ever seen in the history of your career, which is that little dash at the end, which is what you use to remove taint off of a system. Notice it says kubectl taint nodes, node 1 key value equals value 1, no schedule, and then there's a tiny little dash there, right there. So you can use this to take off your taint, right? Don't forget that. I've had a lot of people like, there's no flag to remove a taint. It's like, well, it's there in the man page. It says, put a dash. And they're like, do I put a dash with a space after it? And they're like, nope, you put a dash right after the word. And they're like, that doesn't, yeah, it's not right. Anyway. Notes here that you can't actually retrieve all of the taints on a node and just like take them all off, right? So basically what that does is when you patch a node, you're basically setting the specification for taints to empty. You're basically removing all the taints off a node, right? So with that little bit of JSON. Cool. All right, so let's see this in effect, because it's like, okay, are there moments where I might want to override a taint, where I might still want to like schedule stuff on it? Maybe I need to put forensic tools on there. That's a standard use case, by the way, where a box has been compromised. You're going to taint it. Nothing can go on the system. It's still part of the cluster. Maybe it's isolated, right? And what you can do is then you can like put forensics tools on there. So let's talk about that. So here is what's called a toleration. Tolerations can actually go into a pod specification when you launch a pod. So that way you could put, for example, your forensic tools, whatever, like NCAT or whatever you're using on the actual box. By the way, this is typically how daemon sets end up staying on a system even after they've been marked for evacuation, like not ready or whatever by the system, is that like you won't necessarily get rid of your operations, your security, and your monitoring tools just because the system has entered a not ready state or whatever. You might still keep it on there. So this is the way in which you can like force your operational tools and security tools to stay on a system. Here, here's an example, by the way. So let's say the node is tainted, has listed right here. So it's tainted this way. Now I want you to kind of look at the detail here. This line is actually different than this line. Even though they got the same key and value, the policy is the same. I'm sorry, the policy is different. I'm just over here making stuff up. It's got no schedule and no execute, but it's the same key one and same value one, right? But make sure you note the difference. Those are actually two separate taints. They just have different policies applied, different effects applied to them. Notice it doesn't say prefer prefer no schedule. It says no schedule, no execute. And then there's another key value set here that also has no schedule set up. Now, if you do not write a toleration into your pod spec that has all of this defined, that pod will not schedule onto that system. So here with these tolerations that they have here, this actually looks pretty good. They've got, the key one value one set up with no schedule. They've got the key one value one set up with no execute, but they don't have key two value two with no schedule. They don't have this last one up here. So the pod's not going to run because it doesn't have the third taint. I don't use taints and tolerations a lot. I have used them particularly for forensics investigations. Chris, to add a taint, I'm just checking to make sure you're not messing with me. If you're adding a taint, it's just this. If you want to remove a taint, it's literally the same command with a dash at the end of it. That's the thing I keep ranting about. Yeah. There's like, it would there to be like a little dash at the end here. Oh, you asked on the last slide. Sorry.
I'll just go to voice. I thought it was like when I saw the dash to remove the taint, I thought it was saying like dash no argument. So I thought dash some argument would add the taint, but now I see that it's the opposite.
Yeah, sorry for my tardiness. Yeah. So that literally to convert these in, you just add dashes on the end of them, and that would remove the taint off of it. Yeah. So then that's it. So labels, affinity and anti-affinity, taints and tolerations go together to help like you manage scheduling. Predominantly labels are going to be your primary friend. I highly recommend that, like for complex environments, that you really think about how you're going to manage the delivery and scheduling of pods into clusters, like on particular nodes in the cluster. I will also mention that this is probably why I'm more of a fan of clusters as a service instead of nodes as a service, if that makes any sense. Like I would rather create a GPU-based cluster and a database cluster and a stateless cluster and have the CI/CD pipeline schedule onto the different clusters based on the profile of the app than have to manage a mixed workspace app. But like some customers, like the NFL wouldn't let me do that. They were like, nope. We're running, whatever ridiculous number of pods, 49,000 and change. And this is what we're doing. And we're running it all on one cluster. And I'm like, oh God, really? So, customers win, right? While the customer's not always right, they do always win. So, all right. Oh, and that's it. Okay. Yeah. So that is the end. That's perfect. So reminder, the scheduler is the place where everything starts as far as getting from, past the API server into etcd and then getting scheduled into the actual node. Remember, there's two pieces to the scheduler. There's the predicates and there's priorities. Predicates are non-negotiables. True or false? Do you have the resources to handle me? True. Are you available? True, right? Priorities are like nice to haves. Are you 20, 50, or 80% free on resources? That's what I really want to know. And that works together to give you the score, and then the scheduler will schedule you. If something changes in flight, if it's a predicate, it'll reschedule. If it's just a priority, like something that you could have had, nice to have, it'll let it schedule regardless, right? Labels, affinity and anti-affinity, taints and tolerations are just ways of setting basically labels of differing types against either a node or a pod, so you can control where the scheduler is going to stick things. So that's it. Questions? Okay. Well, here's the fun part. You now get to do a lab on scheduler. So if we switch over to the lab guide and we get rid of lab 7, we let go of lab 8, and we talk about scheduling and node management. So ignore the first part because hopefully your Minikube is still started, right? What's going to happen is the first thing you're going to do is that you are going to you're going to schedule based on node selectors. So what's going to happen is you're going to set up a pod to execute on a specific node using a node selector. So it's going to place on a particular node, and you're actually going to create it before you actually like do anything with the node. And then you're going to label the node with a particular like tag, in this case, quality equals best node. This is your best node, Jimmy. Right. And then you're going to describe the nodes. And then what's going to happen is that all of a sudden the scheduler is going to be like, hey, guess what? We can schedule this. Right. And so you're going to see it pop up. And then you're going to basically like do the same thing with some like CPU limits and requests. So you're actually going to see some interesting YAML here. I will tell you. Yeah. Yeah. Like that could get complicated. I think that's available on the web. I'm not exactly sure, but it's available on the web. And you're actually going to deploy the scalar deployment. You're going to set some replicas, like current replicas and other replicas, create some like dissension, check the state of the deployment. And then you get all your pods and then describe the deployment and then basically describe the node. And notice how like it's going to basically give you some resource contention that you're going to use to basically prevent yourself from launching that last node because you've blocked it from a predicate standpoint. Okay, and that's it. After this, we're going to do accessing applications, which is a little different. So typically, let's see, they usually schedule 45 minutes for this. So feel free to take your run. So let's meet back at 3:45. I'm not going anywhere. Even though if I come off camera, I'm still listening. And we will pick it back up. And then we're going to do a brief chapter on networking. And then we're going to call our day. So if anyone needs anything, let me know. Otherwise, go conquer lab 9. which tomorrow is more Kubernetes, right? More Kubernetes is going to be the day. I think we're going to talk about things like storage, persistent volume, stateful sets, some other pieces along those lines. Based on the way that we're tracking thus far, we'll probably end around 3:30 or 4 tomorrow, even with all of the training stuff and whatnot that I'm going to show you. So, but we'll see how the day goes. Before we move forward into networking, does anyone have any questions about anything we've talked about thus far? Okay. Networking.
Actually, can I get another quick rundown? I know we had talked about it before very specifically, but going through the lab, I kind of lost track of just like kind of the Russian nesting doll situation of what goes inside of what. So just a quick like run through of that real quick would be super helpful to me.
Oh, you
coming
mean
off
like
the lab.
containers versus pods versus?
Yeah, like nodes, containers, pods.
Yeah, actually, we can do that. Let's see. Looks like going out there and seeing. Let's see if we can find a good Kate's. Let's see. Pod. Let's see if we can do this. Container, pod, node, nested. Maybe we can find something like that. Let's see if they have something. No, they don't have something excellent. I should make my own actually, because that would be far more like I think appealing. Let's see what we got here. Some pictures are worth 1,000 words, right? Something that sums it all up. Well, that's actually pretty good. Oh, that's a good one. Actually, let's look up container pod networking. That might be just lead us right to where we want to go. Oh yeah. That's a great one. Hold on. Now I'm just messing around. Let me see if I can find another one. This one? That's pretty good. Hold on. Pod host. Yeah, okay, that's actually a really good one. Let's look at that one. So, isn't that funny? That's in the Kubernetes documentation. 11 ways not to get hacked, right? Interesting. Enable RBAC. But that's a good list, actually. I did not even know that this was here. Running containers does not root users. Here we go. All right. So we'll use networking because we're leading the networking. This is good, right? And I'll use some annotations so we can make sure that this is a little clearer. Okay, so I'll use squares for this. So inside this particular pod, there are containers. Those containers, right, are encapsulated obviously in this deployment method, which is the pod itself in this particular case. Pods can be in a couple of different, like in a sense, workload associations, such as deployments, stateful sets, jobs, cron, like batch jobs, cron jobs, and of course daemon sets. And so that's how pods get deployed. That's how containers get deployed, really, right? And then these pods, which contain containers, say that 5 times really fast, contain containers. They are deployed actually on a variety of nodes. These are worker nodes, of which you can have up to 5,000. You can have as few as 1, right, that are inside the cluster, if you will. And then these nodes are actually part of a whole cluster set. Let's pretend this router gateway thing up here, by the way, is like the leader, right? One of the masters of the primaries. And that would make up the entire cluster. So it goes application, container, pod, node, cluster. Is that helpful? Is that what you were looking for?
Yeah, I think what threw me was we were doing deployment, so I didn't know where deployment fit into it. But now that you kind of described that that's one way to put things on a node amongst many, it makes more sense.
Yeah, so a deployment is just one way to deploy. Stateful sets is another way. Job, also known as a batch job, cron job, and then daemon sets are all ways of telling Kubernetes you want to deploy pods, but each of them has special characteristics. Like a stateful set obviously has the naming persistence that we talked about. Cron job is usually time-based, it runs one time. Deployments are probably the most common way in which stuff gets deployed inside Kubernetes. So deployments are frequent. So, and those just encapsulate the pod deployment. They are like those workloads, because they are pods inside those workloads, they are scheduled on side of nodes. So it's interesting because we could draw another box here and says, hey, you know what? This is actually a deployment. This is a stateful set. This could be a batch job. Good. This is a great opportunity, by the way, using this picture, which actually I'm going to post this link into. It's funny what we discover when we go out there and just Google around, huh? I'll paste this into chat because actually this looks pretty cool. Assuming I'm not going to instantly debug everything that I just typed. Nope, not that. Could have sworn I just actually copied that. There we go. All right. So we're going to use this picture, but we're going to actually go through the material here for a second. Okay. Oh, any other questions? Sorry, anything else anybody wants to ask? Okay. So we already talked about like containers that go inside pods, right? Something that might be interesting is that services are ways of exposing like pods, but services are kind of a separate entity. Like it's almost like a cluster IP address or an IP address on a node or an external load balancer. So just know that services can take on a variety of different shapes, but services' main job is to act as an egress or ingress point, actually an ingress point, sorry, ingress towards a pod or set of pods. Could be multiple pods. Worker nodes and master nodes, also known as primaries or leaders, we've talked about that as 4. And then there's external network, which is the network running outside of Kubernetes, and then external applications, such as like databases or whatnot that are outside of Kubernetes. So the Kubernetes network model is interesting because pods are typically treated like virtual machine hosts. Each pod is going to end up with its own IP address. So if we go back to our little diagram here, notice that down here, you can see that this pod has an IP address, has does this one, has does this one. Now the 10 addresses, the 192.168 addresses, and the 172 addresses in general, I know there's specifics there, are all considered RFC 1918, which means they are private addresses that are not routable across the internet. So you can duplicate these many times over. Many of us are running 192 networks at home or variants, right? If we decide to do that. And so note that these are private IP addresses. These are 10 addresses. Inside that pod, there are containers, and these containers talk to each other off of a very specific IP, like IP address called 127.0.0.1, because in a port number, let's say it's port 80, for example. That's because it is using a local loopback stack. It considers to be everything inside that pod to be one virtual machine, if you will, one virtual network entity. So those guys can all find each other through ports. Now that means, by the way, they can't all be listening on the same port. As you can imagine, if your security tool needs to listen or talk on port 80 and you're running Nginx, that's not going to work, right? At least not internally, right? Between those guys intercommunicating. So note that everything inside the pod is all private. And like, I think there's something in the text where it's like, hey, hold on, where it says like, hey, containers are therefore not 100% isolated from each other, which should be okay in some cases. Let me be clear about this. There's no some cases. It has to be okay in every case, because when you have two containers sitting in a pod, They share memory, they share storage, they share networking. If you put a container in a pod that you don't trust, then you've got a whole different set of problems, because that container is going to have full access, right, to the other container. So yeah, so it's not sometimes, it's in all cases, it needs to be okay. So going back to our picture here. So this has local host networking inside the pod. And then there's an IP address assigned to the pod itself. Now, this is where things get weird. I just want to throw this out there, is that even though every single pod in the entire cluster gets its own IP address, they can find each other, because I want you to note that if you look at those IP addresses, this is 10.0.1.2, 10.0.1.3, 10.0.2.2. Notice that it has nothing to do with the IP addresses that are associated with the hosts. But it does have everything to do with, basically, this is like think of this as like a bridge network or an overlay network, right? There's like a private network here. These guys can find each other, by the way, on different hosts, right? There's like a superset, an overlay network, so they can talk to each other, right? And you can limit that if you want to. So just note that with this little bridge, this is like a virtual bridge that these guys can all talk to each other from. And that's very different from the IP address that's actually assigned to the node itself. Now, what throws this on its side is some of the cloud providers give everything like a public IP address. Like you can give everything a public IP address if you want to, by the way, gets very costly, like from a management overhead perspective, not from a cost perspective. Amazon will give you all the IPv4 addresses you want, right? That they have in their pool, obviously. But sometimes this gets thrown on its side when it's in a managed service provider, but for the most part, these are always private addresses and they get translated to different networks. So one thing to be clear about is that I want you to note that the network that's inside the pod has to be translated to get out to this network, which in turn has to be translated to get to this network. Let me draw that in solid shape so you can see what I'm talking about. This is a network. This is a network. This is a network, right? Because these are different networks here. And then everything outside here is a network. But they know where to find each other when they're local. And if something reaches out, it just comes back in on the same port. So routing and the standard IPv4 networking applies. So it's not like things can't find each other. They can find each other easily. But everything that gets natted or translated out or routed, it knows how to basically flow back in based on where the source traffic came from. So they know how to find each other. Actually, let's change that to red. This knows how to flow back in, right? So here, for example, this guy is trying to get to 10.3.241.152. So note that it's flowing out, hitting the bridge network, getting translated, coming up here. Now this is interesting. What is that pointing towards? 10.100, that's a 10.3. There's no 10.3 over here. Hold on. Hold on, let me see what this picture is doing. Wait, I'm not sure why that would run. I think it's just showing ingress and egress traffic. But like over here, by the way, it's going to 10.0.22. So it looks like it's gotten a little confused about where it's headed, and then it got translated at some point in time. Anyway, if this was the original destination, 10.0.22, then 10.0.22 is over here. So when it hits the router or gateway, it'll say, hey, by the way, if you're looking for the 10.0.2 network, has delineated up here, I need you to go down this way. I need you to talk to 10.100.0.3, which is literally this interface. And then that's going to translate here because this guy knows where that's at, and then it's going to hit 10.0.2.2. So just know that without this little route table here, which says this is where you're going to go, they may not be able to find each other. But just to say this, usually you don't have an external router gateway in play. What happens is that these guys will actually route to each other directly with an overlay network. but that does actually show a good translation of how the networking actually happens, right? The only difference here is that if you don't have a router like in play, what will happen is that these guys will actually just talk to each other directly. They actually know what all the IP addresses are in the cluster, and they'll just route to each other. So Kubernetes handles that directly. So this is actually interesting, like almost like a traditional service derivation. But note that this whole thing is actually not needed for a Kubernetes cluster to run, because Kubernetes will create self-awareness about where all the IP addresses are. Still a great picture though. All right, so let's go back to our official documentation, not that piece. So pods are given an IP address because they're treated like virtual machines. Inside the pods is basically containers that have all this new networking. Yeah, what's funny is that IP routing in NAT is definitely magical, Chris, and actually it's been around forever, since like the 70s, late 70s, 80s. So and of course it's evolved, but it's still pretty amazing. Each pod gets its own IP address. Containers within pods have to expose ports in order for you to be able to get in to the system. Containers in a pod can reach each other on local hosts. We talked about that. Services expose ports to the external network. Kubernetes keeps the list of endpoints current, has pods and services are created and destroyed. That's true. And the API does allow for the discovery of endpoints that it knows about, like that it keeps. So the thing to know is that your application has to bind to a certain port in the container. The container then needs to expose that port out to the pod. Then something needs to actually expose the pod's port out to the external, outside the cluster, which is where services come in. So the container exposes its port, that's exposed from the pod. The pod then now has to expose it out to the internet. The service then has to do that, right? So there's a 3-step process where you're binding the application to a port, the container is exposing it, right? The pod then allows the service to come in and grab it and expose it out. Otherwise, they can just get to it through the pod, but it's not available outside the cluster. Without a service, your applications are not available outside of the pod itself, right? Like, or outside the cluster, actually, that's a better way to say it. So without a service, you cannot expose your applications outside of the cluster. So services are truly for extra networking outside of the cluster. So remember, application binds to port, container exposes the port, right? Then the pod itself is going to expose it mainly in context of, right, a service. That was spectacular. Just sitting in there. Let's go back.
So if it's accepting like traffic over port 80 into, will that always go through a service?
If you're exposing it outside the cluster, yes. If another pod is talking to it, then you don't have to expose it outside the service.
Yeah, I mean, if we were listening to like the internet, it will always go through a service.
It has to be exposed to a service. Remember, services have a couple of different types. So it could be a load balancer service. It could be a cluster IP service. It could be a node port service, but there has to be a service in play. Kubernetes has to expose an endpoint in order for someone outside the cluster to come in. Otherwise, Kubernetes will block it. There's no route.
And do those services, do they always live on like the host of the cluster, or do they live in the nodes?
Nodes are the only thing that can host pods, so they always live on a node.
Okay, I wasn't sure if they were on the pod or if they were on like the master.
The services themselves?
Yes.
Oh, that's a good question, actually. So nothing lives on the master, so I know it's not there. So the service, it depends on the entity. If it's a load balancer service, it's actually external to the cluster because it's a device, unless you've created an ingress load balancer on your cluster, and then it will live there, right? If it's a cluster IP or a node port, then it's an entity that's actually shared across all of the nodes in the cluster. So it's interesting because it's like a virtual service. But if it's got a load balancer, it's there. If it's got an internal load balancer, it's there. Otherwise, if it's a cluster IP or a node port, it's actually a virtual phantom device living in the Kubernetes cluster.
That's what was confusing me, I guess, that it's just a straight up ghost now.
Can I just say that it is confusing because I can't describe it any better than that. I mean, we can go
Yeah.
through and peel it back, but it's like it's like a virtual device.
I was trying to think of like traffic flow coming in and then like deciding which node that we're going to point that to service it. So I was thinking it would make sense for the master to service that, but I'm getting it more now.
Yeah, so the way that works, by the way, is that when you bind a port, let's say it's port 80 is your service and you're not using a load balancer, all of the hosts in the cluster listed on port 80, only one of them has the pod, but all of them know where the pod is at the cluster. So like think of every single node in the system listening on port 80, and if it hits a box that doesn't actually have the pod that's hosting the application, it redirects the traffic to the host that actually does have the pod. So it's a really interesting setup because basically the whole thing acts as a router, acts as a load balancer. All of the nodes, just the worker, like the worker nodes, not the leaders or the masters. Yeah. There's two things that I frequently talk about that are harder in Kubernetes. It's networking and security. Harder, right? So if you're slightly confused, it's okay. But like basically just know that when you use anything other than a load balancer, the entire cluster becomes aware of either the IP address or the port that you're listening to. John, that looks to be like a big, big dog. I can't hear you, but he's got a big head.
It's actually not as big as he looks. It's not that big.
Oh yeah. Yeah, there we go.
It's like a mini lab.
He's still mid-size to large.
Yeah.
And probably all muscle. Yeah. All right, so pods are going to communicate to each other based on their IP addresses. Each pod has a real IP address. I don't even know why they say that. It has a real IP address. It has an RFC internal address, right? It says pod IP addresses are not simply addresses private to the node. They're not private to the node, but they are private to the cluster. So, by the way, sometimes the managed service providers like AWS and whatever will violate that by giving it a public IP address. You can control that, by the way, but like just know that you can't actually put it on a public subnet, and every single pod will grab a public IP address, which that could be problematic from a security standpoint. That is not the recommended way to do it. So, and then pod to service communication. So we talked about services, but this is a way of basically creating a virtual endpoint that either lives on a device like a load balancer, or it lives in the cluster, and it allows you to route load balance across a bunch of different pods. So it acts as a virtual, think of it as a virtual IP address that acts as a static endpoint for you to send clients to. So has basically traffic comes into the load balancer, it redirects to where the pods are inside the cluster. So it's actually cluster aware in that way. And then of course, the other side of the service equation is things are coming in, they're getting redirected to pods. And so remember, you can use either expose or you can apply and create a service. Just know when you create a pod, sometimes people also will create a service object at the same time. So just be mindful of that. What was I doing the other day? Oh, yeah, I was writing some Terraform. If you're not familiar with Terraform, by the way, it's a fun little tool. Allows you to multi-cloud kind of provision resources in cloud providers. And there was just one huge YAML file in there. It was a TF file that basically just created all the objects in Kubernetes, which was actually really nice. But it deployed an application and created the service endpoint, and then it gave you the IP address. I'm sorry, the DNS name, and you could. And if you waited like 2 minutes, the next thing you knew, your application was up and running, and it just did it in like one fell swoop. It was like super awesome. So you can access applications by either shelling into the container, shelling into the container that's next in the same pod as the app that you're looking for. You can actually access on the same node apps in different pods using the app's IP address. You can actually go from pod to pod doing that way. If you're outside the cluster, you have to hit a service. I've already said that repeatedly, so I hope that's like cemented in. You're not going to get into the cluster unless it has a service associated with the pod. And you can also use either the kube proxy or the kube port forward command to forward a port on your local machine through the kubectl command out to the cluster. You can do that as well. Here's some useful commands when it comes to this kind of thing. Minikube, by the way, has, you know, if you want to get the cluster IP address, you can just do minikube IP. If you want the service, like you've created a service and you want to open it in a browser, you just type in minikube space service name, and it will open it up in a browser instantly. If you just want to see the IP address or DNS name, you can do that as well. I'm sorry, I'm not sure why they're listing curl ping and ifconfig. That's not. I'll have to fix that. Hopefully you're familiar with those tools already. Although ping has an interesting history. That's a conversation in and of itself. So all of this, by the way, is happening because of the container networking interface that's inside the system. So just know that it's a plugin, just like the container storage interface, just like the container runtime interface. So we've seen CRIs and CSIs and CNIs, all of which start with container and end with interface. The only change is whether it's a runtime, a storage plugin, or a networking plugin. Now just know that you get to choose your plugins for networking when you load up Kubernetes. There are a lot of choices. That could be a whole class in and of itself. But like Weaveworks has one, AWS has one, there's one called Calico, there's one called Canal. There's all kinds of plugins for how Kubernetes can manage networking. Some of the plugins are more security centric and some of them are more like simple, right? To say that. And so it's used by the container runtimes, right, to basically define how it's going to do networking, right? So it'll call the CNI plugin to basically like set up networking for the container, the pod, the cluster, whatnot. This is probably honestly a little too much. You can actually come in and do configurations against the CNI, but honestly, this is actually done during cluster setup. It's a little too much to go through this actually. If you want to see this on the basically GitHub page, this is the CNI specification, which is similar to the CRI specification, right? Which basically tells you like how this is actually going to function with a container. This is way too much unless you're going to do container development. So I'm just showing you just for giggles. Don't feel like you got to remember this. Like this is a lot. Here, for example, is a CNI configuration where they're using like a bridge plugin, using some authentication mechanism based on a specific IP, setting up DNS and name servers and some other core configuration. Most of the time, you're not going to mess with this, right? When you set up the cluster out of the box, you're going to set up the CNI if you do Kubernetes the hard way, and then you just leave it alone, right? You're not going to come in here and mess with it. So here's the container networking binaries. Basically, you can basically download and clone this container and then set up the CNI plugins if you want. I just want to say is that, again, this is a little bit more Docker centric. The Kubernetes has the same concept, so they're identical. They both use the CNI interface. Yeah, again, you're not going to mess with this. This is going to be defined by your cluster administrator, and you're just going to inherit the CNI plugin that they use. Yeah. Interesting. Let's go take a quick look at some documentation here. All right. So Kubernetes has its own plugins, by the way, which is support a variety of different setups. You can actually extend plugins by using things like KubeNet, which is by default. You can also use things like, what's another one? The AWS VPC. SVPC is another one that sometimes show up. I kind of meant that. Yeah. So the Kubernetes network model allows for these plugins, and these are all the different plugins that you could insert into your cluster. And Treya, Cisco has one. Here's the AWS VPC one. Azure has one. You know, Google has one. Here's Calico and Cilium, and they all have different strengths and weaknesses. In general, administrators are going to use plugins like Calico, Cilium, and Weaveworks because they're just known quantities. So just so you're aware. Paste this in the chat if you'd like to dive into this a little bit more. Okay. Flannel's another popular one. Let's see. Multis is another one that gets used quite a bit. Open vSwitch is very popular with OpenShift. So if you're using that one, it probably has Open vSwitch on it, no VN. WeaveNet is another one that's really popular. So in general rule of thumb, just use what Kubernetes has by default, unless you're looking for some enhancement around security or whatnot. And by the way, if you use a managed service provider, they've written their own. So AWS, Azure, and Google all have their own versions of this. Okay. Good. All right. Well, I mentioned I had a hard stop, so we're going to pause there for a moment. There's probably more to talk about, but does anyone have any questions before we close for the day and I go off to a middle school graduation party? I know, it's laugh worthy. Okay, so I will send out an email when I return that will have the link to the playlist for the videos. Otherwise, I'll see you tomorrow at 8:30. We're going to do a quick review. We'll finish out anything around the networking. We'll do a couple of labs and then we'll move on to the rest of our day with Kubernetes. Okay. All right, everyone. Thank you.